Welcome to Simplilearn's full course on data structures and algorithms, your complete guide to writing faster, smarter, and more efficient code. Let's start with a simple idea. Imagine your computer's memory as a giant bookshelf. How you organize that shelf determines how quickly you can find what you need. Now that's exactly what data structures do. From arrays and linked lists to stacks, queues, trees, and graph, each one has a unique purpose. Arrays keep things in order, stack follows, last in first out, and graph help map real-world connection just like social networks. Today, companies are looking for developers who don't just code but understand how to optimize code. The right data structure can make your program run lightning fast and save valuable resources. So in this course, we will break down the fundamentals, time complexity, arrays, stack, trees, and move on to all the way to binary trees, graph, and popular algorithms that power real applications. We'll also explore modern tools like GitHub Copilot and AI encoding skills that give you an edge. And by the end, you will be ready to write efficient programs, solve complex problems, and think like a real developer. So let's get started. Before we move on, here's a quick information. If you are interested to take your development skills to next level, then our Microsoft AI-powered full-stack developer program is designed to make your job ready in just 6 months. Imagine being able to build dynamic, scalable user interfaces using React, Node.js, Express, MongoDB while also leveraging cutting-edge AI tools like ChatGPT and Copilot to supercharge your code. And the best part is, you will earn official certifications from Microsoft, which will give your resume a significant boost. The program is designed for people who want to get hands-on with coding and understand the full process of developing a modern web app. Plus, you will have access to a Git portfolio, which is perfect for showcasing your work to potential employers. One of the best parts of this program is the AI-powered job assistance. You will get help optimizing your resume and LinkedIn profile, mock interviews to prepare you for real thing, and even custom job opportunities tailored for your skill set. The demand for AI-powered full-stack developers is growing rapidly, and companies are looking for people who can combine traditional coding with cutting-edge AI tools. So hurry up and enroll now, and you can find the course link below.
The term raw data refers to the data in its most basic digital format. After defining data, let's look at what data structure entails. A data structure is a data organization, management, and storage format in computer science that allows for efficient access and modification. Or a data structure is an algebraic structure about data that contains a collection of data values, their relationships, and their functions or operations that can be applied to the data. We will now understand why exactly we need data structures now that we have already defined what is a data structure. So, let us have a look at some of the data structure characteristics. The first one is, each data structure allows data to be stored differently. Following that, the data structure allows for more efficient data search and retrieval. Then, specific data structures are chosen to solve specific problems. Last but not the least, it enables the management of large amounts of data such as large databases and indexing services such as hash tables. Let us now look at some real-world examples of data structures. First and the foremost, we have the dictionary. Assume that we are looking for the word Simplilearn in the dictionary. And we know it begins with the letter S. So we can search for this word beginning with the letter S, and then this is an example of array data structure. As a result, this dictionary can also function like an array data structure. Following by that, we have a music player example. If you have a playlist with 3 songs, the second song will play after the first and the third will play after the second. So these will be played without any interruption because all these 3 songs are linked with each other using linked list type of data structure. So followed by linked list, the next example we have is the data structures. The stack of books analogy is a perfect example of the real-time working of the stack data structure. Subsequent to that, assume there is a line of people at a ticket window and the person who comes first gets the ticket. This particular movie window queue is an example for the real-time implementation of queue data structure. Last but not the least, Google Maps. Google Map is the graph data structure in which all the cities and states are connected. If we want to go from one place to another, there may be many ways to do so. So we can use some algorithms to find the shortest path. As a result, the Google map is a perfect example for the graph data structure working analogy. Following that, we will look at some different types of data structures in this tutorial. So the first type is the linear data structure. The elements in the linear data structure are arranged subsequently one after the other. They are simple to implement because the elements are arranged in specific order. Followed by the first type, the second type is the non-linear data structure, which we will be discussing a bit later. So in linear data structures, we have 4 different types. The first one is the array data structure. Memory elements are arranged in a continuous order in arrays, and arrays elements are of same type. The software program also determines the type of elements that can be stored in arrays. So followed by arrays, we have linked list. Linked lists are completely similar to data structures. Data elements in linked list data structure are linked together by a series of nodes. Furthermore, each node contains the data items as well as the address to the next node. The third data structure is the stack data structure. Elements in a stack data structure are stored using LIFO principle. In other words, the last element stored in the stack is removed first. In stack, operations can only be performed in one end, namely the top. And the last data structure is the queue data structure. Unlike stack, queue data structure operates in the FIFO principle, which states that the first element stored in the queue is removed first. In a queue, insertion and deletion are carried out from opposite ends. Now we will discuss the second type of data structures, which are the non-linear data structures. The nonlinear data structure is the second type of data structure. Nonlinear data structures do not have elements in any order as opposite to the linear data structures. Instead, they are arranged in hierarchical order, with one element connected to one or more others. So the first one in the nonlinear data structures is the tree data structure. A tree data structure is built using nodes and edges. Each element in the tree data structure is called as node or vertex. Each vertex or node is connected to the other nodes or other vertices using edges. And the second one in the list is the graph data structure. A graph data structure is completely like a tree data structure. It also has the vertices and edges. Each vertex in a graph data structure is connected using edges. The only difference between a tree and graph is that in tree you can have n number of vertices, but in graph you will have only 2 vertices. After discussing the graph data structure, we will move ahead into the last segment of this tutorial, that is importance of data structures. So the first one, data structures are widely used in almost every aspect of computer science, both for simple and complex computations. Next, data structures are used in all areas of computer science, including artificial intelligence, graphics, big data, operating systems, and much more. After that, the data structures are an essential component of many computer algorithms because they allow programmers to manage data efficiently. Lastly, a proper data structure selection can improve the efficiency of a computer program or algorithm.
Introduction to time complexity. The time complexity of an algorithm is the amount of time it takes to run as a function of the length of the input. The length of the input determines how many operations the algorithm will do. It will provide the information about the variance, increase or decrease in execution time as the number of operations in an algorithm increases or decreases. Next up, types of time complexity. We will start with the constant time complexity. Then we will discuss linear, logarithmic, quadratic time complexity. Now let's have a look at them in the detail. First, constant time complexity. When an algorithm is not reliant on the input size n, it is said to have constant time of order big O of 1. The runtime will always be the same regardless of the input. As you can see in the code, every line has the runtime of 1. And they are all independent of any input size, so the runtime is always constant. Next up, linear time complexity. When an algorithm's running time increases linearly with the length of the input, it is said to have linear time complexity. When a function checks all the values in an input data set it is said to have the time complexity of order of big O of n. As you can see in the code, the loop depends on the size n. So the time complexity rose up to n. Next up, logarithmic time complexity. When an algorithm lowers the input data in each step, then it is said to have the logarithmic time complexity. Binary trees or binary search functions are some of the algorithms with logarithmic time complexity. As you can see in this code, by finding out the mid in every iteration, the runtime will decrease every step, making it approximately logarithmic runtime. Next up, quadratic time complexity. When the execution time of algorithm rises non-linearly up to n square with the length of the input, it is said to have quadratic time complexity. In general, nested loops falls into the quadratic time complexity order where one loop takes big O of n, and if the function contains the loop inside the loop, then it multiplies. As you can see in this code, because of the nested loops, the time complexity rose to n square. Now that you have the firm grasp of time complexity and its type, we will discuss essential steps to evaluate the time complexity. To understand this, we will take an example of Fibonacci number. This code prints the Fibonacci numbers till n. We will divide this code into three parts, isolating all the loops that play a significant role in altering the time complexity. Let's look at the first part. It consists of some independent statement which give constant time for each statement. Next, let's move on to our next part, that is for loop. Since this loop runs n times, this will give linear time complexity on n. Next up, the third part, which also has the constant time complexity. Now, let's take a total of runtime, which comes out to be n plus 5. We will then discard the constant part to find the time complexity, which does not affect the overall time complexity. Now, we will have the final time complexity of big O of n. We have now discussed time complexity and how to evaluate it. Now, let's have a look at the time complexity of various algorithms. We will look at the time complexity of insertion sort, merge sort, quick sort, bubble sort, and some searching algorithms like linear search and binary search. Let's look at them in the detail. First up, insertion sort. As you can see in this code, we are using nested loops. So in worst case, its complexity comes out to be n square. Now in the best case scenario, the complexity will be linear time complexity. Next up, merge sort. In this case, whether it is the worst case or the best case, it will always remain n log n, as every statement in this code will run the same amount, so no matter what, its time complexity will remain the same. Next up, quick sort. The time complexity of quick sort in the best case is n log n, and in the worst case it is n square. Next up, bubble sort. As you can see in this code, we are using nested loops. So in the worst case, its complexity comes out to be n square. Now in the best case scenario, the time complexity will become the linear time complexity, that is n. And after that, we will discuss some of the searching algorithms. First up, linear search. In the best case scenario, if the statement to be searched is at the first position, then the time complexity will come out to be constant. Whereas in the worst case, the time complexity will come out to be n. Finally, binary search. In the best case scenario, if the element is to be searched is at the mid, then the time complexity will come out to be the constant. Whereas in the worst case scenario, the time complexity will come out to be big O of log n. We have now discussed the time complexity and how to evaluate, and the time complexity of various algorithms. Now let's sum up what we have learned from this session. First up, the execution time increases with the types of operations we make using the inputs. Next up, the lesser the time complexity, the faster is the execution. Finally, if a code is of hundreds of lines, then it takes a toll on the PC's processor. So it is essential to check and reduce the time complexity as much as we can. Let's get started with what are pointers. A pointer is a variable that points to an address of another variable. It is declared using a star symbol, also called asterisk, and then we allocate a memory of a variable to it. We can access a variable's address using the ampersand symbol in the same manner as the pointer declaration. Let's write a code. We will declare a variable a is equals to 5 and a pointer ptr. Then we will assign this variable a's value to pointer ptr. Now let's write a print statement to directly access the variable's value using variable name. Let's write another print statement to print the value of a using pointer. Let's try and execute this program. As you can see, we have successfully accessed variables value using both variable name and pointers. Let's get back to our slides. Now, let's discuss different types of pointers. First up, null pointer, void pointer, while pointer, and dangling pointer. Let's discuss these in details. First up, null pointer. It is a kind of pointer that points to a null memory. As you can see in the figure, here is a pointer which is pointing to a null memory. To get a better understanding, let's try a simple program in the code editor. Let's write a code. First we will declare a pointer var. Then we will assign its value to null. Now let's try to print this statement. Let's execute this. As you can see, since this pointer points to a null or nothing, that's why it doesn't print anything. Let's get back to our slides. Next, void pointer. When a pointer is created with data type void, then this pointer is called void pointer. If we want to print the variable's value, then we have to typecast this pointer to avoid any error. For better understanding, let's get back to the code editor and try it with a simple code. First, we will declare an integer variable a is equals to 5 and a void pointer ptr. Now we will assign address of a to pointer ptr. Let's write a print statement to print this pointer. Let's run this program. As you can see, we are getting an error that's because we can't print a void variable. To print this, we have to typecast this variable to integer. Let's do this. We can typecast a variable like this. Now let's print this. As you can see, we can print it now. Let's get back to our slides. Next, while pointer. When we create a pointer but don't initialize it by assigning any memory to it, then this kind of pointer is called while pointer. These pointers can be very tricky. They can even cause a program failure or a segmentation fault. Let's get back to the code editor and try it with a simple code. First, let's declare a pointer ptr. But we will not assign it with any address. Let's write a print statement to print it. This time we will directly print it. Let's execute this. As you can see, we are not getting any results because there is no value assigned to it. Sometimes it may even throw segmentation error. Let's get back to our slides. Next, dangling pointer. Let's suppose there is a pointer p which is pointing at a variable. Now, if we deallocate this memory using a free function, then this pointer will point at a free space or a non-existing memory. Then this pointer will become a dangling pointer. To get a better understanding of this pointer, let's try it with a simple code. Let's declare a pointer ptr. Here we will dynamically allocate memory using a malloc function. To do this, we will put int star in a bracket, then malloc function, then in another bracket we will put memory size to be allocated. Now let's declare a variable a and assign its address to the pointer. Now to make it a dangling pointer, we have to deallocate the memory of this pointer. We will use free function for that. Now let's write a print statement to print this pointer. Let's execute it. As you can see, since we have deallocated its memory, that's why it is pointing to nothing. Hence, it doesn't print anything. Let's get back to our slides. Till now, we have discussed pointers, ways to access variables, and types of pointers. Now, let's talk about use cases of pointers. We will talk about pointer arithmetics, pointer to pointer, array of pointers, call by value, and call by reference. Now, let's dive right into it. Let's talk about pointer arithmetics. We can use four arithmetic operations on pointers: increment, decrement, addition, or subtraction of an integer from a pointer. Since pointer operates on addresses, it only makes sense if we apply pointer arithmetics on sequential data structures like arrays or strings. Let's discuss them in detail. First up, increment. If we apply this operator on a pointer, then it will shift this pointer's address to its sequential successor. As you can see in the figure, As we increment the pointer's value, we shift to the next index of the array. Let's get back to the code editor and try it with a simple program. Let's declare an array of size 3. Let's give them some value. We will then declare a pointer and assign it to the array's first element. Now let's write a for loop to traverse this array. In this for loop, we will increment a pointer's value and print this pointer's value to traverse this array. Let's try and execute this program. As you can see, we have traversed this complete array. Let's get back to our slides. Next, decrement. If this operator is applied on a pointer, it will shift this pointer's address to its sequential predecessor. As you can see in the figure, as we decrement this pointer, we also shift to array's previous index. Let's get back to the code editor and try to implement it. Let's declare an array of size 3 and assign it some values. Now let's declare a pointer and assign array's last element's address to it. Now let's write a for loop to traverse this array. In this for loop, we will decrement the pointer's value Also, we will keep printing this pointer's value to traverse this array. Let's try and execute this program. As you can see, we have traversed this complete array from the back. Let's get back to our slides. Next, the addition of an integer to a pointer. If this operator is applied on a pointer, it will leap forward accordingly. If the integer is 2 and our pointer points at the first element, then the pointer will sequentially skip one element and shift to the next element. Let's implement it in the code editor. Let's declare an array of size 7 and assign them some value. Then declare a pointer and assign it to the array's first element. Now let's take an integer n to add in the pointer. Now let's write a for loop to traverse this array. In this for loop, we will increment the pointer's value with integer n and we will keep printing the pointer ptr's value. Let's execute this code. As you can see, we have traversed this complete array skipping one element at a time. Since we have skipped 3 elements, that's why we are getting last 3 values as garbage values. Let's get back to our slides. Next, subtraction of an integer from a pointer. If this operator is applied on a pointer, then accordingly it will leap backward. If the integer is 2 and our pointer points at the last element, then the pointer will skip one element and shift to the previous element. Let's try and implement it in the code editor. First, let's declare an array of size 7 and assign it some values. Then declare a pointer ptr and assign it to the array's last element. Now let's take an integer n to subtract from the pointer. Now let's write a for loop to traverse this array. In this for loop, we will decrement the pointer's value with integer n. Also, we will write a print statement to print this ptr's value. Now let's try and execute this program. As you can see, we have traversed this complete array from back, skipping one element at a time. Since we have skipped 3 elements, that's why we are getting last 3 values as garbage values. Let's get back to our slides. Let's talk about precedence of these operators. Operator asterisk and ampersand have the same priority as the unary operator increment and decrement. These operators are evaluated from right to left. Let's understand this concept with an example. Suppose if a pointer p points to a variable x, then we can swap x with pointer p in that expression. In the first row, we have y is equal to x plus 1, which means we are storing an incremented value of x in y. Similarly, if we replace x with a pointer p, we can store incremented value of pointer in y. In row 2 and row 3, we are incrementing x and storing incremented value in x itself. We can do this with pointers as well. In row 4, we are attempting to execute pre-increment with a pointer p. In row 5, we are attempting to execute post-increment with pointer p. Here we have to put star p in braces because these operators are evaluated from right to left. So to give more priority to pointer p, we have to use braces as they have highest priority. Let's talk about another use case, pointer to pointer. Basically, in this situation, a pointer will point at a variable via another pointer. We declare it with two asterisk symbol. Let's discuss it with an example. Suppose a pointer 1 points to a variable and another pointer 2 points to that pointer 1. This way, pointer 2 will indirectly be pointing to the variable. Let's go to the code editor and try implementing it. First, we will declare a variable var a pointer ptr1 and a pointer to this pointer ptr2. Then we will assign this variable var's address to ptr1 and ptr1's address to ptr2. Now we will write a print statement to print variable var, ptr1 and ptr2. Now let's try and execute this program. As you can see, ptr1 and ptr2 shows variable var's value as ptr2 is pointing to ptr1 and ptr1 is pointing to that variable. So indirectly ptr2 points to the variable var. Thus it prints the variable's value. Let's get back to our slides. Let's discuss the array of pointers. As the name suggests, it is an array that has all its elements as pointers. These pointers can be pointing at another array. It is declared as an array with asterisk symbol. Let's discuss it with the program. First, we will declare an array A of size 3. Then we will declare a pointer array ptr of size 3. Now we will write a for loop to assign A's element's address to ptr's element. Then we will write another for loop to traverse ptr and print its element. Let's try and execute this program. As you can see, it prints the value of array A's elements because array ptr's elements are pointing to array A's elements. Let's get back to our slides. Next, call by value. We don't use pointers in this concept, but it is very important to understand this concept to get better understanding of the next topic, call by reference. In call by value, we call a function and directly pass the variable's value as parameters. In this situation, a copy of those variable is created and get passed into a function as parameters. If we modify these parameters, it will not affect actual variables. Rather, these copies will get deleted as soon as the function body ends. Let's try implementing it in the code editor. Let's write a code. First, we will declare a variable x equals to 100. Then we will write a function call to function func with argument x. Next, we will write a print statement to check if any changes happened due to the function. Now, let's write definition for this function. We will take a void function with argument as x. In this, first we will set x equals to 200. And then we will write a print statement to print this value. Let's try and execute this program. As you can see here, when we get back to the main block from function, its value again reverted back to 10. Because in call by value program, we only pass variables copy into the function, not the actual variables. Let's get back to our slides. Next, call by reference. In this, if we call a function, but this time we pass the variable's address as parameters, then in this situation, actual variables will get passed into the function as parameters. If we modify these parameters, it will modify the actual variables even outside the function scope. Let's try implementing it in the code editor. First, we will declare a variable int x equals to 100. Next, we will write a function call for function func with argument as address of x. Then we will write a print statement to check if any changes happen due to the function. Now let's write definition for this function. It will be a void function with argument as pointer x. In this, we will first set x equals to 200. Then we will write a print statement to print this value of x. Now let's try and execute this program. As you can see, this time variable x's value didn't revert 200. That's because in call by reference we pass actual variable's address to functions, so it will modify them as well. Let's get back to our slides. During the course of this video, we have learned a lot about pointers. Let's discuss some advantages of the pointers. First up, pointers are useful to access a memory location. Pointers are also an effective way to access the array elements. Pointers are used for the dynamic memory allocation and its distribution. Pointers are also used to build complex data structures like linked list, graph, tree, stack, queue, etc. Now, let's talk about some disadvantages as well. First up, pointers are difficult to understand, so a programmer needs to be careful while handling them. They might raise some errors like segmentation error or access some unrequired memory and cause program failure. If a pointer is pointing to an incorrect value, then it might corrupt memory. Pointers may also cause memory leakage. Also, pointers are slower than variables. At last, let's sum up what we have learned in this session with key takeaways. First up, a pointer is simply a storage location for a data in a memory. We can use pointers to traverse array more efficiently. We can also use function pointers to call a function dynamically. We can perform arithmetic operations on pointers as well. When we define an array of pointers, its elements can also point to function, making it easier to call different functions at once.
Why did we actually need an array? So to understand this, let's go through a simple concept. Let us imagine that we have some data and the data is related to students, right? So if we wanted to store the marks of individual students, then we had to declare a variable for each of the student. So you can see we have student 1, student 2, student 3, 4 and 5 and their individual scores. So the score 1 is assigned to student 1 and so on, with student 5 being assigned to score 5. So in the real time, this might be a little clumsy. We have here just 5 students, so that is okay. But what if we had 500 students or 5,000 students, right? That might be an issue. There we have to create some 500 or 5,000 variables, and it would be a little tough to handle that, right? Even if we wanted to apply some operations collectively on all the variables, that might be a little tedious. So what if we had one variable which could store all the 5 students or 500 students or 5,000 students all together and make it really easy for us to apply some operations collectively on all the students, right? This sounds a little bit logical. So similarly, we do have a data structure which can do that, which can collectively store all the data elements in it as a single variable. and it will also help us to apply the operations which are logical or mathematical on all the variables and their values together as a whole. So that is the purpose why we had created arrays. That is the purpose why we needed arrays. So far we have understood what was the necessity for arrays. Now we will understand what exactly are arrays. So basically an array is a linear data structure that stores the elements in a sequential manner, one after the other. And when you declare an array, the variables will be stored one besides the other, that is adjacent to each other in a sequential order. Now let us understand how the array is represented by the compiler. Now the next part, that is the memory representation of arrays. Now let us imagine that we have declared an array which stores character type data. And another important point to remember about arrays, when you declare an array, it stores only a single data typed elements only. For example, here we have declared a character type array, right? So we cannot store integer type data or float type data in it. We only have to save character type array or character type elements in this particular array. So now let us imagine that we have created an array which is of character data type, and these are the elements which are A, R, R, A, Y. Now how does the compiler represent it in the form of memory? So when you create an array, these are formed, that is the index values and the address. So basically compiler will select a block of memory and it has addresses to that block, and it can be anything. Right here we have 11, 12, 13, 14 and 15, and in real time it might be 1001, 1002, 1003, 1004, 1005. The main motto is assign a sequential block of memory, and this is the array and the elements are A, R, R, A, Y, and this particular one, which is the last one, is the index of the array. That is the position of the array for user. So using this index, you can access the elements in the array. More on that in the accessing part. So let us imagine that we wanted to access the element R. So how to access it? We might not know the address, right? In that instance, we will use the index. This is for R reference. So we will tell, I want the element from array index number 2, and then we'll have the ARR, R element. So in the practical form, this is how we use the index. Now let's continue with the lower bound and the upper bound. So the first initial location is called as the lower bound, and at the last or the max value of the array is called as the upper bound. Now let us jump into the next topic where we will understand the different types of arrays. So these are the different types of arrays: one-dimensional arrays and multi-dimensional arrays. In multi-dimensional arrays, we have two more types, that is two-dimensional arrays and three-dimensional arrays. So how are arrays different from each other, right? So the first one, we'll deal with the first one, that is the one-dimensional array. Now, how is an array declared as one-dimensional? For that, we need subscript. So one-dimensional array requires only one subscript to specify the number of elements in an array. So how is it actually represented? So here you can see an example right on my screen. So here is how a one-dimensional array looks like. So here we have the data type, that is integer data type, and marks is the name of the array, and this is the size of the array, and here the elements will be stored, and here it is the index value of the array. And remember, the index value of array always starts from 0. In the previous example, that was only for basic understanding, so I just started that with 1. In the practical way, the array index always starts from 0. So followed by the one-dimensional array, we will deal with the multi-dimensional arrays. In that, we have the following. The first one is the two-dimensional array, and the second one is the three-dimensional array. In the multi-dimensional arrays, we require more than one subscript. In the previous example, we had one-dimensional array, so the subscript is just 1, that is 10 columns, right? So we just had one single row and 10 different columns. But in the multi-dimensional arrays, we need multiple rows and multiple columns, right? So we need 2 subscripts for two-dimensional array and more than 2 subscripts for three-dimensional arrays. So first we have the two-dimensional arrays. The 2D array is organized in the form of a matrix which can be represented as a collection of rows and columns. So here is the example. As you can see on my screen, we have 3 columns and 3 rows. And we have 2 subscripts that define the number of rows and the number of columns and the elements in each and every row. So the 1, 2, 3 confines the first row, 4, 5, 6 confines the second row, and 7, 8, 9 will be the third row. Now similarly, we have 3-dimensional arrays. A 3D array is a collection of 2D arrays which consists of 3 subscripts: block size, row size, and column size. So here we have an example for that. So we have 3 subscripts. That is, the first one is block size, the second one is the row number, and the third one is column number. So this happens to be the first block, this happens to be the second block. And this is how a 3-dimensional array can be represented. Now we have the next stage where we will understand how to declare the arrays. And the syntax is right on my screen. You need to specify the data type of the array, which is integer, float, or character, any selection which you make. Followed by that, you need to select an array name for your array, and inside that, you need to declare the array size. And sometimes you can also eliminate the array size if you wanted to, have a dynamic array. And here is an example for that. You have integer data type, name of the array is example, and the array size is 6. So the compiler will allocate continuous memory block of 6 integer type blocks. So these are the few more methods to initialize the array. So here you can see integer data type, array name is A, element size is 5, and we have 5 elements. The method 2 is, remember I have said you can eliminate the size of the array, right? So here you can use this way as well, integer data type, array name A, and no size here, and you can directly declare the elements. And the method 3. So here you have the name of the array, size of the array, and you are allocating the elements to the individual memory locations. This is also another method to initialize array. And method 4 is using a for loop. You can just initialize a for loop and the I value will be stored in the array locations starting from 0. Now let us understand how to access the elements in an array. So to access the elements in an array, you need to specify the name of the array and memory block where you have that element that you want to access. So here we have an example, which is integer data type, name of the array is xyz, and the element we wanted to access is 5. So here we have an example that is integer type array name is xyz, and it has the size 5. And now we wanted to access the first element in an array. That can be done using the first index, that is xyz of 0 index, that is the first element, and accessing the second element, and so on. Xyz of 1 will be the second element, xyz of 2, 3, 4 will be the third, and fourth and fifth elements. Now let us understand some basic operations that can be performed on the array elements. So the following are the operations that can be performed on the array elements, that is the traversal, insertion, deletion, searching, and sorting. Now let us get into practical mode and try to execute some examples based on traversal of the array, insertion of an element into the array, deletion of an element from an array, searching for an element in an array, and sorting the complete array. So at first we'll carry out the traversal operation. So here we have an array that is A of 5 and the elements are 1, 2, 3, 4 and 5. Now we're going to use a for loop to traverse through this array and print all the elements sequentially. Now let us execute this code and see the output. So as you can see, the code got successfully executed and the elements, that is 1, 2, 3, 4 and 5 from the array A are printed sequentially. Now moving ahead, we'll try to execute some examples based on insertion of element into the array. So on my screen you can see an example for inserting an element into the array at the starting position of the array. Now let us try to execute this code and see the output. Don't worry about the codes. These code documents will be attached in the description box below and you will be able to have an access to it and run these codes in your personal laptop and get a better learning experience. Now you can see the code got successfully executed and now it is asking for the size of the array. Let's declare it as 5 and now let's enter the elements into the array. Now it is asking for the element to be added at the beginning of the array. Now we have 2, 3, 4, 5 and 6 existing in the array. Let's add the first element 1 and there you go. The resultant array is 1, 2, 3, 4, 5 and 6. The element which we added at the ending, which is 1, is supposed to be in the first or the beginning part of the array, which is here at the first index location as planned. Now let's get started with another example on the insertion. Now let's try to insert an element at any given location as per the user's choice. So as you can see, we have a program on my screen and running this program must help us to insert an element into any given location of the array. Now let's try to quickly run this program and see the output. So there you go. Enter the elements into the array. Let's enter 1, 3. Let's try to run this program and see the output. So there you go. The program got successfully executed and now the output is asking for us to tell it the number of elements in an array. Now let's say 4 elements. So now let's enter the 4 elements. 1, 3, 4, 5 and 6. Okay. So the 4 elements, which is 1, 3, 4, 5 are been inserted. Now it is asking for the location where you want to insert the element. Now let us insert it in this second location. Now let us set the value as 2 and there you go. The resultant array is 1, 2, 3, 4 and 5 and the element, which is 2, was supposed to be added in the second location and it has been successfully added. Now let's try to execute another example based on insertion where you will try to insert the element in the last position. Now this program on my screen will help us to add an element at the end of the array. Let's quickly run this program. Now it is asking for us to enter the 5 elements of the array. Let's enter that. Now it is asking to enter the element to be inserted. Now let us enter the element and this element should be added at the end location as discussed. The resultant array is 1, 3, 5, 7, 9 and 11. Now let's continue with the deletion operation. Now the program on my screen is an example for deleting an element from the beginning position of an array. Now the program got successfully executed and it's asking for us to enter the size of the array. Let's enter the size as 5. And now let's enter the elements of the array, that is 1, 2, 3, 4 and 5. Now the element from the first location, that is 1, has been deleted and the resultant array is 2, 3, 4 and 5. Now the code on my screen will help you to eliminate the element from the ending location of an array. Now let's try to quickly run this program and see the output. So you can see that the program is successfully run and it is asking for us to enter the size of the array. Let's enter 4. Now let's enter the elements of the array, that is 1, 2, 3 and 4. Now after eliminating the last element from the array, that is 4, we have the resultant array, that is 1, 2 and 3. Now a little homework for you guys. Let's try to execute an example for deleting an element from any location of an array. This will be a homework. Now don't worry, try on your own, and if you don't get that, you can refer to the comment sections below where you have the code document attached in the description box and you can refer to it. Now let's continue with the next operation where we will search for a given element in the array. So you can see that on my screen we have an example which will help us to sort the elements in an array. Let's quickly run this. So there you go, the program got successfully executed and now it's asking for the array size. Let's enter 5 and now let's enter the elements in a random order. Now the resultant array should be sorted. So there you go. The array after being sort is, it's 2, 3, 5, 14 and 21. So there you go, the array got sorted. So now we have finished our practical session. Let's have a quick overview again. So traversal in an array is a process of visiting each element once. Traversal can be done by various means, that is by counting the array elements, printing the values sorted in the arrays, and sum of all elements present in the array, and many more. So this is how we traverse our array from the first location to the last location. Again, the insertion operation. Insertion in an array is the process of including one or more elements in an array, and it can be done at the beginning, at the end, and at any given index of an array, which we executed for all the three types of examples. Now next we have the deletion operation. So deletion operation or deletion of an element is a process of removing a desired element and reorganizing the array, and it can be done at the beginning, at the end, and at any given index. So we have executed the example for at the beginning and at the end, and the homework was at the given index. Don't worry if you don't figure it out, you can always refer to the example document which is mentioned in the description box below. Now the search operation. Searching is a process of finding a given value in the list of values, and it decides whether the search key is present in the array or not, and we have executed an example on that. And again, the sort operation, where we will sort the given array. If the given array is not in the default order or in a given order, that is ascending or descending, then we can sort the order of the array by the user's choice, given it is ascending order or descending order. Now in the next section of the tutorial, we will discuss the advantages of using arrays. So the first one is array stores multiple elements of same data type with same name. Next one, elements in an array can be accessed randomly using just the index number. Array memory is predefined, so there is no extra memory loss. Array avoids memory overflow. And finally, 2D arrays can represent the tabular form of data in a very efficient way. Now let us also have a look on some of the disadvantages of using arrays. The first one, the number of elements in an array should be always predefined. So there is no chance that you can add some extra element in the last moment. Array is static in nature, so its size cannot be varied after declaration. What if, consider that you wanted to store 10 student data in one array and you end up having just 7 students. So the remaining 3 is a waste, right? So you are wasting memory there. That's the problem. And insertion and deletion operations in an array is quite difficult as the array stores elements in a continuous form. And finally, allocating excess memory than required may lead to memory wastage. Now we have the final key takeaways of the arrays. So we discussed why do we need arrays, then we discussed what are arrays, followed by that we discussed types of arrays, next we had a declaration of arrays, accessing elements from an array, initializing the arrays, and basic operations on array, that is the practical demo part, and finally we have discussed the advantages and disadvantages of using an array. What are arrays? So we will see a brief definition of arrays. The array is a data structure that stores elements of the same data type in a sequential order. Two-dimensional arrays are considered as an array of arrays. Two-dimensional arrays represent the information in the form of rows and columns, which is completely similar to a tabular form of data. Following by the definition and briefing of the two-dimensional arrays, we will understand the need for two-dimensional arrays. So the main advantage of using a two-dimensional array is the elements can be represented in the form of a matrix, that is rows and columns. Using two-dimensional arrays, we can initialize, access, and print multiple elements in the matrix form by just running one single code segment. You can see an example right on my screen here. This is an example of marks list. Suppose a class has 3 subjects, namely English, Science, and Maths. We have 4 students and we wanted to represent the data in the form of a database. So here, the marks of the 4 students can be represented using two-dimensional arrays. Now, we will see the syntax of a two-dimensional array. So here, the syntax. At first, we need the data type. The data type can be integer, character, float, string, etc. Then we have the name for the two-dimensional array. And later, we can have two subscripts which represent two dimensions, that is, the rows and columns. The first subscript defines the number of rows and the second subscript defines the number of columns. And note that the column number can never be null. And at the end, we have a semicolon to terminate the syntax. And here we have some examples of two-dimensional arrays. So in the first example, we have the name of the two-dimensional array and we have 3 rows and 4 columns. And followed by that, we have another example which is of character data type and the name of the array is names and we have 7 rows and 15 columns. Next, we will see how to visualize two-dimensional arrays. We read earlier that two-dimensional arrays are a collection of rows and columns. Let's see an example of two-dimensional array. We will consider an array with 6 rows and 4 columns. As you can see on my screen, we have integer type array and the name of the array is array and we have 6 rows and 4 columns. The product of rows and columns will give us the total number of elements present in a two-dimensional array. In the current example, we have 6 rows and 4 columns and the product is 24. So we must have 24 elements in this array. Next, we will see how to initialize two-dimensional arrays. So there are two ways to initialize a two-dimensional array. So in the first method, we declare the elements in the set of curly brackets. This array consists of 3 rows and 3 columns. Note that the index always starts from 0. Here we have 3 rows. It means the row starts with 0 and ends with 2. The same goes for the column. But sometimes this method might be a little confusing. So we have a better method. The advantage of this method is clarity. We can visualize all the elements with better clarity compared to the previous method. So the first 3 elements are 9, 6 and 1. They are present in the first row. And in the second row, we have 144, 70 and 50. They comprise the second row. And finally, the third row in which the elements are 10, 12 and 78. So far, we have learned how to visualize and initialize a two-dimensional array. So we have done it by using the index values, that is the row index and the column index. So the row index value was 3 and the column index value was 3. For accessing an element in the two-dimensional array, we need to pass the name of the two-dimensional array followed by the row index value and the column index value. For example, let us assume that we wanted to access the element 9. For doing so, we will pass the name of the array followed by the row index value and the column index value as shown below. That is int first 0, 0. And an important point here is indexing always starts with 0. We will now start printing the two-dimensional arrays. So to print a two-dimensional array, we will be using 2 nested for loops. So to understand the process of printing the two-dimensional array, let's get back to the practical mode and we will work on a code. So on my screen, you can see an example for two-dimensional array. So here we have declared an array with the name first and we have 3 rows and 3 columns. And inside that, the first row of elements is 9, 6, 1 and the second row of elements is 144, 70 and 50 and the third row of elements is 10, 12 and 78. Followed by that, we have 2 counter variables which are I and j. So we are using the first counter variable I in the outer for loop and the second counter variable j in the second inner for loop. And inside the inner for loop, we have a print statement which is used to print the elements in the array. Now, let us try to execute this code and see the output. So you can see the code got successfully compiled and we have our elements here, which is 9, 6, 1, 144, 70, 50, 10, 12 and 78. Now let us understand the logic. So here we have declared the counter variable as 0 and the condition is I should be less than 3, which is true. So the control will enter into the second inner for loop. Here we have j is equals to 0 and j should be less than 3, which is true. So here the condition or the statement is valid and it will print the first element 9. Followed by that, j will be incremented again. J is now equals to 1 and j is less than 3. So again, we'll print the second element, 6. Again, j value will be incremented to 2, so 2 is less than 3. Then we will print the third element, that is 1. Now when you increment the value of j from 2 to 3, the condition will fail because 3 cannot be less than 3. So the control will enter into the outer for loop. Here we have I value is equals to 0, which will be incremented to 1. So 1 is less than 3. Again, the control will enter the inner for loop. Here again, we will check for j is equals to 0, which is true. So we will print the second row of elements, that is 144, 70, 50, in the same way how we printed the first row, right? So j will be equals to 0. So then we'll print the first element. So j will be incremented to 1 and 1 is less than 3. Then we will print the second element, that is 70. And again, j will be incremented to 2 and 2 is less than 3. So we will print the third element, that is 50 in the second row. And again, j will be incremented to 3 now. The compilation of the condition will result in false. So it will exit the second for loop and it will come back to the first outer for loop. Now the value of I will be incremented to 2. So 2 is less than 3. The control will enter into the inner for loop again. Then we will print the third row of elements. That is 10, 12 and 78 in the same way how we printed the first row and the second row. After printing the third row, the condition will fail when j value is incremented to 3 and it will enter the outer for loop. Here the I value will be incremented again from 2 to 3 and the condition fails. Now the overall control will come out of both the for loops and it will terminate here. So that's how we got 9, 6, 144, 70, 50, 10, 12 and 78. So with that we have come to the conclusion, and so far we have learned the following things. What are two-dimensional arrays? Why we need two-dimensional arrays? Syntax of 2D arrays, visualizing 2D arrays, initializing 2D arrays, accessing 2D elements, and finally print the elements of two-dimensional arrays.
Let's get started with what is linked list. A linked list is a linear data structure made up of nodes. These nodes consist of two parts, data and reference to another pointer. Typically, a linked list starts with a head node, which goes all the way up to the last node, which is called tail. Next, let's discuss why do we need linked list. A linked list is a linear data structure like arrays, but an array can only offer a fixed size, whereas a linked list can dynamically increase its size. Also, operations like insertion and deletion are much easier in a linked list than in an array. Now, let's try to implement the linked list in the code editor. Let's start by creating a node. To create a node, we need a class. Let's declare a class node. We will declare its member as public. The first member is int data and the second member is node pointer next. Now we will go into the main block and initialize our first node. To initialize a node, we need to use node star. The node name head equals to null. Similarly, we will create more nodes. and our last node tail. Now we will allocate these 4 nodes in the heap. To do that, we will use a node name equals to new node star, new node braces. Now we will allocate all the nodes in the same manner. Now we will assign data to our first node. To access the member of the node class, we will use arrow formation. Then we will use data equals to, let's give it a value as 2. Now we will link this first node with our second node. To do that, we will use add, same arrow formation, and next, which will be equals to our n1 node. And now we have created our first complete node. Now let's create other nodes as well. N1 arrow data is equals to, let's give it 3. N1 arrow next is equals to N2. N2 arrow data is equals to 5. N2 arrow next, 2 arrow next is equals to tail. Now tail is equals, tail arrow data equals to 7, and tail arrow next is given null. Now let's call up function to print this list. We will give head as the argument, as we can only traverse a linked list from its head. Let's write a definition for this print list function. This function will be a void function. Argument is node star a. We will use while loop to traverse this linked list. We will give it condition if a is not equals to null, then cout is a data and L. Now we will change our cursor from the current node to the next node. To do that, we will use a is equals to a arrow next. Now let's try to execute this code. As you can see, we have traversed our complete linked list. Now let's get back to our slides. Now let's discuss different types of linked list. The first are singly linked list. Next is the doubly linked list, the circular linked list, and finally we have the circular doubly linked list. Let's discuss each one of these in details. First up, singly linked list. It is a unidirectional linked list. While using the singly linked list, we can only traverse it in one direction, that is from head node to the tail node. Next up, doubly linked list. It is a bidirectional linked list. We can traverse it in both the directions. In this linked list, the node has an additional pointer that points to the previous node. Next up, circular linked list. It is a regular linked list except for its last node points to the head node. Programmer needs to be careful while traversing it, or they might get stuck in an infinite loop. Next up, the circular doubly linked list. It is a combination of doubly linked list and a circular linked list. Its last node points at the head node and the previous pointer of the head node points to the last node. It is also bidirectional linked list so that we can traverse it in both directions. We have now discussed the linked list, why do we need linked lists, and types of linked list. Now let's learn about some operations we can apply on linked list. We can use majorly two operations on linked list. First up, insertion and deletion. We can perform these operations in three different situations. First, at the beginning, at the last, or at a specific position after a node. Next, we will discuss these operations in detail. First up, insertion. We will discuss first insertion at the beginning. We have to give the first node's address to the new node's next pointer to execute this. Next up, insertion at the end. We have to give the new node's address to the last node's reference pointer. Next up, insertion at a specific position. To do this, we will have to change the reference address of the previous node to the new node's address and the new node's reference pointer to the next node's address. Now, let's discuss deletion. First up, deletion at the beginning. We have to change the first node's address to the null to execute this. Next up, deletion at the end. We have to change the second last node's address to the null. Next up, deletion at a specific position. We will change the reference address of the previous node to the next node's address. We have learned a lot about linked list during this session. Now let's discuss some benefits of linked list. First up, a linked list is a dynamic data structure. That is, we can dynamically increase its size. Next, it offers easy insertion and deletion than other linear data structures like arrays and string. Since it can dynamically increase its size, resulting in no memory wastage. Next, it is pretty handy in implementing complex data structures like stacks and queues, etc. Now, let's talk about some disadvantages as well. First up, since the linked list is made up of nodes, it takes extra storage for storing data and reference pointer. Next, the traversal in the linked list is a bit harder than other data structure. Reverse traversing is easy in doubly and circular doubly linked list, but since it uses one extra pointer, it takes extra storage, making it another limitation. At last, let's sum up what we have learned in this session with key takeaways. First up, we have recognized linked list as a dynamic data structure. Next, a linked list offers faster insertion and deletion operation. Next, Linked list traversal is hard because we have to start from the head node every time. Finally, a linked list is an asset in implementing other data structures like stacks and queues. Let's get started with introduction to single linked list. A single linked list is a linear data structure made up of nodes. These nodes consist of two parts, data and reference to another pointer. These nodes can be traversed using pointers. It starts from the head node all the way up to tail node. Now let's try to implement the single linked list in the code editor. Start by creating a node. To create a node, we need a class. Let's declare a class node. We will declare its member as public. The first member is int data and the second member is node pointer next. Now we will go into the main block and initialize our first node. To initialize a node, we need to use node star. The node name head equals to null. Similarly, we will create more nodes. And our last node tail. Now we will allocate these four nodes in the heap. To do that, we will use a node name equals to new node star, new node braces. Now we will allocate all the nodes in the same manner. Now we will assign data to our first node. To access the member of the node class, we will use arrow formation. Then we will use data equals to, let's give it a value as 2. Now we will link this first node with our second node. To do that, we will use add same arrow formation and next, which will be equals to our n1 node. And now we have created our first complete node. Now let's create other nodes as well. N1 arrow data is equals to, let's give it 3. N1 arrow next is equals to n2. N2 arrow data is equals to 5. N2 arrow next 2 arrow next is equals to tail. Now tail is equals tail arrow data equals to 7 and tail arrow next is given null. Now let's call up function to print this list. We will give head as the argument as we can only traverse a linked list from its head. Let's write a definition for this print list function. This function will be a void function. Argument is node star a. We will use while loop to traverse this linked list. We will give it condition if a is not equals to null, then cout is a data and l. Now we will change our cursor from the current node to the next node. To do that, we will use a is equals to a arrow next. Now let's try to execute this code. As you can see, we have traversed our complete linked list. Now let's get back to our slides. We have now introduced the single linked list. Now let's discuss some of the operations we can apply on a linked list. First up, insertion. We can perform insertion at three different situations, like at the beginning, at the last, or at a specific position after a node. Next up, deletion. Similar to the insertion, we can perform it in three different situations as well. At the beginning, at the last, or at a specific position after a node. Let's talk about them in detail. First up, insertion at the beginning. To execute this, we have to give first node's address to the new node's next pointer. Next up, insertion at the end. To execute this, we have to give new node's address to the last node's next address. Next up, insertion at a specific position. To execute this, we will change the previous node's reference address to the new node's address and the new node's reference pointer to the next node's address. Now, let's try these operations in a code editor. As you know, a linked list is made up of nodes, so we should start by creating a node. To create a node, we need a class node and we will define its members as public int data and node pointer next. Now we will create a function to insert a new node in front of the list. For this function, as an argument, we will give the reference to the head of the list and integer new data. Now in the definition we will allocate a node new node equals to. Now we will put in the data in the new node. We will use arrows to access the data equals to new. Now we will make the next of this new node as head. Now we will move the head to point to the new node. Now we will create another function to insert a node after a specific position. As arguments, we will give it the address to the previous node and and the integer new data. We will first check if the given previous node is null. If it is, we will print given node cannot and then we will return the function. Otherwise, we will allocate a new node and then we will enter the new data in that. Now we will make the next of the new node as a next of the previous node. And then we will move the next of the previous nodes as new node. Now we will write a function to insert a node at the end of the list. As an argument, we will give it a node pointer to pointer head and integer new data. We will first allocate a new node. We will also create a last node and give it head. Now we will put in the data in the new node. Since this new node is going to be the last node, so we will make its next as null. Now, if the linked list is empty, then we'll make the new node as head. To check that, we will use if star head is equals to null. If it is, then we will do star head equals to new node. Else, we will traverse it to the last node while last next not null. Last is equals to last next. Now we will change the next of the last node as new node. Return. Now we will write a function to print this list. While node is not null, see out node arrow data handle and node equals to node. Now we will write the code for the main block. First, we will define a head node and mark it as null. Now we will start using those functions to make a linked list. First, we will use append function to add 6 in it. Next, let's use another function push and add 7 in it. Now we will try to insert 1 at the beginning. So we will use push again, comma 1. Now let's try to insert 4 at the end. So far the list looks like 1, 7, 6, 4 null. Now let's try to insert 8 after 7. To do that we will use insert after. As argument we will use head next as 7 is present next to the head, comma 8. Now let's try to print this linked list. Cout created linked list print list add return 0. Let's execute this. As you can see, we have created the linked list in the correct order. Let's get back to our slides. Now, let's talk about deletion. First up, deletion at the beginning. To execute this, we have to change first node's next address to null. Next up, deletion at the end. To execute this, we have to change the second last node's address to the null. Next up, deletion at the specific position. We will change the previous node's reference address to the next node's address. Now, let's try these operations in a code editor. We will start by creating a class node. In this class, we will declare the members as public int data and the node pointer next. Now to insert the data in the node, We will use a function push as argument. We will give pointer to pointer node head and integer new data. We will allocate a new node we will give this new node the data as new data and new nodes next as head. Now we will write a function to delete the node. As argument, we will give a node pointer to pointer head and int key. Now we will store head in a temp node and we will create a node prev as null. If head node itself holds the key to be deleted, we will use if temp is not equals to null and temp data is equals to key. Then head equals to temp next. Now we will free the old node. Else we will search for the key to be deleted. Else while temp is not equals to null and temp data is not key, So prev equals to temp, and temp will be iterated to its next. If the key is not present in the linked list, then we will just return the function. Else we will unlink the node from the linked list. And delete. Now we will write a print list function to print the list. Its argument will be a node pointer node, while a node is not null. Cout less than node data. Then we will iterate this node using node equals to node next. Now we will move on to the main block. We will start with the empty list node star head equals to null. Now we will add the element to this list. So push ampersand head comma 7. Next push percent head comma 2 push ampersand head comma 5. Next push ampersand head comma 9. Now cout created list print list head Now we will use delete node function. Delete 2. We will use argument as ampersand head comma 2. Now we will check the linked list of 2. Print list. Let's try and execute this. As we can see, we have deleted the 2 from the linked list. Let's get back to our slides. At last, let's sum up what we have learned in this session. First up, we have recognized singly linked list as dynamic data structure. Next up, the singly linked list offer faster insertion and deletion operation. Next, singly linked lists are unidirectional linked lists. That is, you can only traverse it in one direction. Finally, a single linked list is an asset in implementing other data structures like stacks and queues. Let's get started with an introduction to Doubly linked list. A Doubly linked list is a linear data structure made up of nodes. This linked list is a bidirectional linked list, that is, we can traverse it in both directions. These nodes consist of three parts. First up, data, reference to the next node, and reference to the previous node. Now let's try to implement the doubly linked list in the code editor. As you know, a linked list is made up of nodes. So we will start by creating a node. To create a node, we need a class node. Its members should be defined as public. Int data, node pointer, next, and node pointer ref. Now we will write a function to insert a node at the beginning of the doubly linked list. Void push. The argument will be a node pointer to pointer, add, and int new data. Now let's allocate a node, node star, new node equals new node. Now let's put in the data into the new node. Since we are adding at the beginning, its previous is always null. Now we will link the old list of the new node. Now we will change the previous of the head node to the new node. We will check if head is not null, then heads previous is equals to new node. Now let's move the head to the point to the new node. Now let's write a function to print the given doubly linked list. Its argument will be a node. We will iterate it until the node is not null. Out node data and and node equals to node next. Now let's write a code for the main block. We will start with the empty list. Now we will use a push function to push values in the function. Another push function head comma 3, push function ampersand head comma 5, push function head comma 7. Now out doubly linked list then we will call the print list function print the doubly linked list. Let's execute this program. As you can see, we have successfully created our first doubly linked list. Let's get back to our slides. We have now introduced doubly linked list. Now let's discuss some of the operations we can perform on a doubly linked list. We can perform three operations on a doubly linked list. First, traversal, insertion, and deletion. We can perform a traversal in two ways, a normal traversal and reverse traversal. And we can perform insertion and deletion in three different situations: at the beginning, at the last, and at a specific position after a node. Let's discuss these in detail. First up, normal traversal. We can traverse a doubly linked list using a next pointer starting from head to all the way up to tail node. Reverse traversal. Similar to the normal traversal, we will use previous pointer. We will start from the tail node to go all the way up to head node. Now let's try to traverse the doubly linked list in the code editor. Let's start by creating a class node. We will define its members as public, int data, node pointer, next, and node pointer ref. Now we will write a function to insert a node at the beginning of the doubly linked list. Void push. Its argument will be a node pointer to pointer head and integer new data. Now we will allocate a node star new node new node parenthesis. Now we will put in the data. Since we are adding at the beginning, so its prev is always null. Now we will link the old node to the new node. Now we will change the previous of the head node to the new node. Now we will move the head to the point to the new node. Now we will write a function to traverse the linked list normally. Void traverse node pointer while loop node is not null, therefore cout node data node equals to node next. Now we will write a function to reverse traverse it. Its argument will be a node pointer to pointer head. We will create a node tail equals to head while tails next is not null. This loop is enabling us to reach to the tail node so that we can traverse it from backside. Now, while loop until tail is not equals to head out tail tail equals to tail rev. Out tail data handle. This last cout statement is only because we are not traversing till the head pointer. Now let's go to the main block. Let's start with an empty list. Node star head equals to null. Now let us create a linked list to test the function. So we will use push function head comma 2, another push function ampersand head comma 3, push head comma 7. Since we are inserting at the beginning, so the actual linked list looks like 7, 5, 3, null. Now we will print the original linked list first. Cout original traverse head cout reverse traversal reverse traversed linked list Now let's try and execute this program. As you can see, we have traversed it in the normal way as well as the reversed way. Let's get back to our slides. Next up, insertion at the beginning. We will create a node with the previous pointer pointing to a null and the next pointer pointing to the head node. Then we will change the head node's previous pointer to the new node and we will change the new node to the head node. Next up, insertion at the end. We have to give the new node's address to the last node's next pointer and change the new node's previous pointer to the last node. Next up, insertion at a specific position. We will change the previous node's next pointer to the new node and the new node's previous pointer to the previous node and the next pointer to the next node and vice versa. Now let's try these operations in a code editor. We will start by creating a class node public node pointer rev node pointer. Now we will write a function push insert a node at the beginning of the list. Its argument is node pointer to pointer head into new data. We will first allocate a new node star new node equals new node parenthesis. Now we will put in the data node arrow data is equals to new data. Now we will make the next of the new node as head and previous as null. and new node previous is equals to null. Now we will change the previous of the head node to the new node. First, we will check if the head node is null. Then star head previous equals to new node. Now I will move the head to the point to the new node. Now let's write another function to insert a node after a specific position. Void insert after argument will be node pointer prev node int new data. We will first check if the given previous node is null. Yes, then we will give it cout a given node can't be null, and we will return to the function. Or else we will allocate a new node equals to new. Now we will put in the data. Now we will make the next of the new node as the next of the previous node. Equals to ref node Now I will make the next of the prev node as new node. And make the prev node as the previous of the new node. Now I will change the previous of the new node's next node. if new node next not null, then new node next rev is equals to new node. Now let's write another function. Insert a node at the end of the list. Void append argument will be a node pointer to pointer head int new data. First we will allocate a new node equals to new parenthesis. Now we will create another node last equals to head now we will put in the data new node data equals to new data. Now since this new node will be the last node, so its next will be null. If head is equals to null, new node rev equals to null and star head is equals to new node. Return. Or else we will traverse till the last node while last next is not null, last equals to last next. Now we will make the last node as the previous of the new node. Return. Now we will write a print list function to print this list. The argument is a node pointer node, while node is not null, out node data node is equals to node next. Now let's write the main block. We will start with an empty list. We will start by inserting 6, so the linked list becomes 6 null, and ampersand head comma 6. Now we will insert 7 at the beginning, push ampersand head comma 7. Now we will insert 1 at the beginning also. Now we will insert 4 at the end. Till now the linked list looks like 1, 7, 6, 4, null. Now we will insert 8 after 7. So insert after head next comma 8. Now let's print this linked list. Let's try and execute this. As you can see, we have created our linked list in the correct order. Let's get back to our slide. Next up, deletion. First up, deletion at the beginning. We have to change the first node's next to null and second node's previous to null. Next up, deletion at the end. We have to change the second last node's next pointer to null and delete the previous node to free up the space. Next up, deletion at a specific position. We will change the previous node's next pointer to the next node and next node's previous pointer to the previous node. Now, let's try these operations in a code editor. We will start by creating a class node public int data node pointer next node pointer ref. Now we will write a function to delete a node in a doubly linked list. Void delete node. Its argument as pointer to the head node. Repeat. Its argument as pointer to the head node pointer. And pointer to the node to be deleted. Now we will check the base case condition, that is if head is null or the node to be deleted is null, then return now if the node to be deleted is a head node, then head is equals to del now if next node of the del not null, that is if the node to be deleted is not the last node, then else next previous equals to else previous. Now we will change prev only if node to be deleted is not the first node. So if del prev not equals to null, then del prev next equals to del's next. Finally, we will free the memory occupied by the del. Free del. Now let's write a function to insert a node at the beginning of the doubly linked list. Void pointer to the head node pointer and int new data. We will allocate the node. Now we will put in the data. Since we are adding at the beginning, so prev is always null. Now we will link the old list of the new node. Now we will change the prev of the head node to the new node. Now we will move the head to the point to the new node. Now let's write print list function. Node pointer node while node is not equals to null. layout, node, data, node equals to node next. Now let's get started with the main block. We will start with the empty list. Now we will create new nodes, push %head, comma 2, push ampersand head, comma 4, push ampersand head, comma 6, push ampersand head, comma 8. Now let's print this list. Cout original list, original list. Now we will call the print list function head. Now we will delete the node from the doubly linked list. Here we are deleting the first node. Next, let's delete the last node. Now the modified list should look like 4, 8, let's try and print this. Cout modified list head. Let's try and execute this. As you can see, we have deleted all the nodes except for 6 and 4. Let's get back to our slides. At last, let's sum up what we have learned in this session. First up, we have recognized doubly linked list as dynamic data structures. Next, the doubly linked list offers faster insertion and deletion operation. Next up, doubly linked lists are bidirectional linked list. That is, we can traverse it in both directions. Finally, a doubly linked list is faster at reverse traversal. Let's get started with introduction to circular linked list. A circular linked list is a linear data structure made up of nodes. It is like a singly linked list except its last node points at the head node. These nodes consist of two parts, data and reference to next pointer. These nodes can be traversed using the next pointer. Now, let's try to implement it in the code editor. We will start by creating nodes. To create a node, we need a class node. We will define its members as public, int data, and node pointer next. Now, let's write a function to insert a node at the beginning. Void push we will use arguments as a pointer to node pointer head and int data. We will define a node, new node equals to new node parenthesis star head. Now we will put in the data into the new node. Since we are inserting at the beginning of the linked list, that's why this new node's next should be the head pointer. If linked list is not null, then set the next of the last node as head. While temp next is not equals to head, the temp is equals to temp arrow next. Now temp next equals to new node. Else new node next is equals to new node. Star head equals to new node. Now let's write a function to print this linked list. Void print list node star head node star temp equals to head. If head is not equals to null, then do cout temp data temp equals to temp next. Now while temp is not equals to head, this condition is important to stop this loop so that it doesn't go infinitely. Now let's go to the main block. Let's initialize this list as empty. Node star head equals to null. Now let's insert some nodes in this linked list. Push ampersand head comma 2, push ampersand head push ampersand head comma 11, ampersand head comma 5. Now this linked list looks like 5, 11, 9, 2, then it will again go back to 5. Now let's try to print this. Cout circular list head. Now let's try and execute this. As you can see, we have successfully created our first circular linked list. Let's get back to our slide. We have now introduced the circular linked list. Now let's discuss some of the operations we can apply on a circular linked list. We can perform two operations on a circular linked list. First up, insertion. We can perform insertion at three different situations: at the beginning, at the last, and at a specific position after a node. Next up, deletion. We can perform deletion at the three different situations. First up, at the beginning, at the last, and at a specific position after a node. Let's discuss these in detail. First up, insertion at the beginning. We have to give the first node's address to the new node's next pointer to execute this. Next up, insertion at the end. We have to give new node's address to the last node's reference pointer. Next up, insertion at a specific position. We will change the previous node's reference address to the new node's address and the new node's reference pointer to the next node's address. Now let's try these operations in a code editor. So far we have implemented a linked list using classes. Now let's try to implement it using structures. We will start by creating a struct node with its element as int data and struct node next. Now we will write a function which can only insert a node to an empty list. Struct node star add empty. Struct node star last comma int new data. Now since this function is only for the empty list, so we will have to check if the linked list is empty or not. If last is not equals to null, then we will return last. Now let's create a node dynamically. Struct node start temp equals to struct node star malloc size of struct node. We will copy this statement because we will need it in the future functions. We will assign the data to this new node. Temp data is equals to new data. Last is equals to temp. Now we will create the link. To do that, we will use last next is equals to last. Since we are in an empty list, so the first node will always point to itself. Return struct node start. We are creating a function to insert at the beginning of the linked list. Struct node star add begin. As argument, we will use struct node comma int data. If last is equals to null, then we will return add empty last comma data. Now we will create a node dynamically. I've already copied this statement for the ease. Now we will put in the data. Data is equals to data temp next is equals to last next last next is equals to return last. Now we will write a function to insert a node at the end. Struct node star add and struct node star last int if last equals to null, then return add empty last comma data. Now we will dynamically create a node and put in the data. Temp data equals to data temp next is equals to last next. Now last next is equals to temp and last equals to temp. Return. Now we will write a function to insert a node after a specific node. So struct node star add after struct node star last comma int data int item. This item is a node after which we have to insert the node. If last equals to null, then return null. Struct node star temp comma star p is equals to last next. Now do if equals to item temp equals to we will dynamically create a node here. Temp is equals to struct node star malloc size of struct node. Now we will put in the data. So temp data is equals to data temp next is equals to next. Now p next is equals to temp. If p is equals to last, then last is equals to temp. Return last. Equals to p next. While not equals to last next. Cout item not present in the list. Return last. Now we will write a function to print this list. Void print list struct node star last struct node star p. Now if last is equals to null, then cout list is empty and return. Else, we will point to the first node of the list. So P is equals to last next. To traverse the list, we will use do while loop. So do cout data is equals to P next. While P is not equals to last next. Now let's write a code for the main block. We will start with an empty list struct node star last equals to null. Now last is equals to add empty last comma 6. Last equals to add begin last comma 4. Last equals to add begin last comma 2. Last equals to add end last comma 12. Last equals to add after last comma 10 comma 4. Print list let's execute this. As you can see, we have created the linked list in the correct order. Let's get back to our slides. Now, let's talk about deletion. First up, deletion at the beginning. We have to change the first node's address to the null to execute this. Next up, deletion at the end. We have to change the second last node's address to null to execute this. Next up, deletion at a specific position. We will change the previous node's reference address to the next node's address. Now, let's try these operations in the code editor. Let's get started with creating a node. To create a node, we need a class node. We will declare its members as public int data node pointer next. Now we will write a function to insert a node at the beginning of the list, void push a pointer to the node pointer head and int new data. Now let's create a node and make head as next of it. Node star new node equals to new node parenthesis. Let's put in the data new node data is equals to new data and new node next is equals to head. If linked list is not null, then set the next of the last node as the first node. If star head is not null, then we will find the node before head and update next to it. So node star temp is equals to star head while temp next is not equals to head, temp is equals to temp next. Now temp next equals to new node. Else new node next is equals to new node and star head is equals to new node. Now let's write a function to delete a given node from the list. So void delete node. Its argument is a pointer to the node pointer head and int key. Now if linked list is empty, then we will simply return it. If star head equals to null, then return. Otherwise, if head head data is equals to key and head next is equals to head then free head head is equals to null. Return. Now node last is equals to star head comma star d. Now if head is to be deleted, then star head data is equals to key, then while last next not equals to star head, then last is equals to last next. Now we will point the last node to the second node of the list. Now we will free this head star head equals to last next. Now if either the node to be deleted is not found or the end of the list is not reached, then while last next is not equals to head and last next data is not equals to key, then last equals to last. If node to be deleted was found, then if last next data is equals to key, then d is equals to last next and last next is equals to d's next. Now we will free d. or else C out no such key found. Now let's write a function to print this list. Void print list node star head node star temp equals to head if head not null then do cout temp data temp is equals to temp next while temp is not equals to head. Cout now let's write a code for the main block. We will start by empty list. So node star head equals to null. Now we will push ampersand head 2 push ampersand head comma 5 push ampersand head comma 7 push ampersand head comma 8 and push ampersand head comma 10. Now we will print the list before any deletion operation. Cout list before deletion print list head. Now let's delete head. Let's delete 7. Cout list after deletion print list head. Let's execute this. As you can see, our deletion function is working perfectly. Let's get back to our slides. At last, let's sum up what we have learned in this session. First up, we have recognized circular linked lists as dynamic data structures. Next, the circular linked lists offer faster insertion and deletion operation. Next, a circular linked list are unidirectional in nature. That is, we can only traverse it in one direction. Finally, a circular linked list traversal is quite tricky as we have to stop the loop as soon as we revisit the first node. Otherwise, it will traverse it indefinitely.
So at first, what exactly is an array? So an array is a linear data structure that stores homogeneous data elements in a continuous form. So homogeneous in the sense, you will be able to store only one single data type of elements in an array. For example, consider that you have declared an array and you wanted to store some elements in the array. So you can declare a data type first, after that the name of the array, and if you declared that the array should store integer data type, then you can only store integer elements in that particular data type. You cannot store any other data type like float or character. That is the meaning of this particular definition. And it stores the elements in a continuous order, that is in the adjacent format, as you can see in the example here, 10, 20, 30, 40, and which are located in the adjacent locations, that is 0, 1, 2, and 3. Now let us understand what exactly is a linked list. So similar to array, even a linked list is a linear data structure. But the only difference is it is a dynamic data structure. Here, you can increase or decrease the size of the linked list in runtime. The only difference is here the memory locations are not adjacent to each other, but they are taken from the memory heap. So there is a huge memory chunk. Out of that, the linked list will borrow some of the memory locations, and one after the other, the memory nodes will be interconnected using pointers. So that was the difference between array and linked list. And similar to arrays, even the linked list store homogeneous type of elements. That is, if you declare a linked list of float data type, then you can only store float data type in it. You cannot store any other different data type like character or string. Now followed by that, let us understand the types of arrays. So basically we have three different types of arrays. Those are the one-dimensional arrays, and inside multi-dimensional arrays we find two more types. Those are the two-dimensional arrays and three-dimensional arrays. Now one-dimensional arrays will be having only one subscript, that is, they'll be having only one single row. Whereas in the two-dimensional arrays we will be having two subscripts, that is, it will be having rows and columns. And in the three-dimensional arrays it will be having three subscripts, that is, the row, column, and the block address. Now, followed by the types of arrays, we will understand the types of linked lists. So similar to arrays, even linked lists are divided into three types. They are singly linked list, doubly linked list, and circular linked list. The difference between them is a singly linked list will have two parts, that is the node address and node element. In this particular segment, the element will be stored, and in this particular second segment, the address that points to the next node will be saved. And similarly, in the circular linked list, the only difference between the singly linked list and the circular linked list is, at the end of the singly linked list, you can see a null pointer which indicates the end of the linked list. But in circular linked list, the address will not be null. Instead, it will point back to the head node. That is what which makes it as a circular typed singly linked list or a circular linked list. When it comes to the third type, that is the doubly linked list, we can see there are two address locations. The first starting node will have null as its first address location, then we'll store the element, and the second address location will point to the next node. And you can see in the second node will have element, and the first address location will point to the previous node, and the second address location will point to the next node. And at the end, the second address location will be pointed as null, which indicates as the end of the linked list. Now that we know the types of linked list and arrays, we will look into the fundamental differences between arrays and linked lists. So the first fundamental differences between the arrays and linked list is, the array element can be accessed randomly using just the index values. But whereas random access is not possible in linked list. If you want to access any element in linked list, you need to perform the traverse operation sequentially. The second difference between the both is, array is static, which means memory size is fixed, which cannot be changed in runtime. But whereas in the linked list, the memory is dynamic, which means you can either shrink or expand the memory in runtime according to your requirements. Followed by that, the next difference is, each element in array is independent in nature. That is, you can access any element just by giving the index location. Whereas in linked list, the elements are interdependent on each other. Whenever you want to access a specific element, you need to go through the other elements or traverse through the other elements. Next one is, the array takes more time in operations like insertion and deletion, whereas linked list takes less time to perform the operations of insertion and deletion. Followed by that, the next difference is, accessing any element is faster in array as random access is possible, and the array data structure just by using its index values. But whereas accessing an element in linked list is slow, because we know that we need to traverse through all the node elements to access a particular element. Now the next difference is, in case of an array, memory allocation is done in compile time. Whereas in linked list, the memory allocation is done during the runtime. Memory utilization is inefficient in an array as it is allocated as in static and it is allocated during the compile time. In case of linked list, the memory utilization is very efficient as the memory is allocated during the runtime.
What is a stack? So basically, stack is a linear data structure just like arrays and linked lists. The only difference is that it follows a specific order when an operation is implemented on it. So what is the specific order that it follows? That is LIFO, last in first out, or FILO, first in last out. In the next parts, we will understand this order in a much better way. All operations can be done only at the one end of the stack, that is on the top. Now we will discuss much about that in the operations part of the stack. Now let us understand the first fundamental, that is the representation of stack. That is, how do you represent a stack normally? So a stack can be represented using two different methods, that is using an array or using a linked list. So in an array, we will be using the continuous memory. And in stack, we will be using a non-continuous memory, and the stack will behave like a dynamic stack or a dynamic data structure. Now the first method, that is the array method. So in this method, an array is used to represent the stack. As you can see in the image below, we have a stack. So the name of the stack is stack itself, and you can see two more things here, that is top is equals to 2 and max is 4. So the max is the value of the array or the length of the array, the maximum length of the array, and top is the position where the last element of the stack is present. Here in this case, 56 is the last element in the stack and top is inclined, or it is addressing to that particular address, that is 2. And now let us discuss about the linked list representation of stack. So in this method, a dynamic data structure, that is a linked list, is used to represent the stack. This representation leads to a dynamic stack. It does not need to define the maximum number of elements present in the stack. Remember, in arrays, we had to define the max value. In the previous example, we had the max value as 5, but in here, you need not to assign the max value as the stack itself is dynamic. The pointers links are used to store the address of the upcoming nodes, and the variable used in this method is top. So the top is holding the address of the topmost element in the linked list representing the stack. Now moving ahead, we shall understand the basic operations on stack. Now here, we will understand the previously discussed definition, that is push, pull, etc. in a much better way. So the basic operations on a stack are push, pop or pull, and peek. Now let us discuss each one of them in a detailed way. The first one is push operation. So the push operation is the mechanism of inserting a new element into the stack. As you can see, we are trying to insert the elements from the top. So the push operation basically involves the following steps. Check if the stack is either full or not. So basically, whenever you're trying to insert an element into the stack, you need to make sure that the stack is empty or it has some space. If it is full, you cannot insert an element into the stack. Step 2. If the stack is full, produce an error and exit. That's what I was talking about. Now the step 3. If the stack is not full, increment the top by 1. That is, when you're inserting an element, then you need to update the top value. For example, in the previous slide, when we had the array representation of a stack, we had the top value as 2. So if you try to include an element into the stack, then you need to update the top value from 2 to 3. That is incremented by 1. Now the fourth step, add data elements to the stack where the top is pointing. And finally, success. The push operation has been successful. So this is how you insert or push an element into the stack. Now followed by push operation, we have pop or pull. So the pop operation is a mechanism of eliminating or deleting or removing one data element from the existing stack. So we shall understand the pop operation in a much more detailed way. The operation involves checking the stack is empty or not. If in case the stack is not empty, then you can carry forward the pop operation. But in case if the stack is empty, then you have to provide an exit status and exit the control and leave the stack. So if the stack is not empty, approach the data element at the top, that is at the top position. For example, in the previous array example, remember, right, we had the top position pointing towards 2. So you need to take the control to the top position and pick out the element and pop it. And finally, decrease the top by 1. So when you eliminate the top element, then the top value from 2 will be decremented to 1. So this is how the pop operation is carried over on a stack. Next one is the peek operation. The peek operation involves returning the topmost data element from the stack without moving it. So here you can see the top is pointing to the element number 4 and you're peeking the element number 4 and you're not removing it from the stack. You're just returning the topmost data element. You're passing the value of the top element. So to understand the push, pop and peek operations on stack in a much more better way, let's carry out a practical example. Now we are on the practical mode and here you can see on my screen we have the code example for the stack. Now first we'll be checking if the stack is empty as per the steps mentioned in the previous discussion. We will check if the stack is empty or not. If it is empty, then we will return, else we will continue. And again, another step, we also check if the stack is full. If the stack is full, we will exit, else we will continue with the operation, whatever it is, peek, pop or push. And here we have an example for the peek operation that we discussed previously, and followed by that we have a pop operation. We are trying to exclude an element from the stack.
And another one, we have the push operation where we'll be trying to push the elements into the stack. So these are the three functions for push, pop, and peek. Now we'll try to push in the elements and also pop and try to involve some functions on it or run some operations on the stack. Now let's run this code and see the output. So you can see that the code has successfully executed and we have the statements here. The first one says the stack is not full, that is false, and stack is empty, that is true, right? And after that you can see that the elements which we tried to push into the stack, that is 11, 76, 71, 15 and 66 are been pushed into the stack. And if you clearly observe it, we have the element 11 in the bottom, 76 upon that, 71 upon that, and 15 and last 66. So the order is first in, last out. That is, the first element was pushed first, and when you are trying to eliminate the elements from the stack, then you will first pick out 66, followed by that you will pick out 15, followed by that you will pick out 71 and so on. So this is the rule what stack follows. Now I hope I made myself clear with the example. Now we shall continue with the applications of stack. So these are the few applications of stack. The first one is expression conversion. So you can see we have the infix notation, prefix notation and postfix notation. So the infix notation is no rocket science. There is only one thing here to learn, that is we have two operands A and B, and we have one operator, that is the addition operator, in between those two operands. And when you use the prefix notation, you will have the operator located at the first place, then you will have the operands followed by it. And in the postfix one, you will have the operands first, and followed by the operands you will have the operator. So basically all the infix, prefix and postfix notations give out the same results, but the only difference is the representation of those operands and operators. Now let us understand this in a much more detailed way. So conversion of expression from one form to another form is the main application of stack. So we have the first one, that is infix to prefix and infix to postfix. Now let us see an example. Here you have 1 plus 2 star 3 plus 4. So this is the normal infix notation. And when you try to present the same expression in the form of prefix notation, so this will be the result, and this is the result for postfix. The next one, prefix to postfix and prefix to infix. And this is the way you write the prefix notation, and if you want to convert that to infix, this is how you can write it. And this happens to be the result of postfix notation. And finally, postfix to prefix, postfix to infix, and these are the results. Now followed by expression evaluation, the next important application of stack is checking parentheses. And you can see if the parenthesis is set properly, the expression gets evaluated. If not, it will not be evaluated. Now the last one, memory management and function call. The very useful thing of using a stack is the memory will not be allocated to your stack elements unless the function is called. Here you can see it is the main function, and these are the elements that you wanted to declare into your stack. And unless you make a function call, the elements will not be declared their memory, or the elements will not get the memory allocated for them. Now another good application of stack is the backtracking problem, or the n-queen problem. The n-queen problem is an example of backtracking problem. The n-queen solution to this problem is to position the queen in such a way that the opponent queen cannot attack your queen. Now another example is string reversal. You can see on my screen we have a string that is A, B, C, D and E. Now using stacks you can reverse this, right? So you're basically eliminating an element and relocating it to the first place. And finally, after reversing your string, this will be your result, A, B, C, D and E. Followed by that we have conversion evaluation. So stack is used to evaluating the expression as shown in the example. Since parenthesis has the highest precedence, 5 plus 4 gets evaluated first, and it will result in 9. then multiplication and division have the same precedence. Now the associativity comes into picture. So the associativity is always from left to right. So first 4 into 9 will be executed, which will result in 36, and then 32 divided by 4, which will give us 8. Now we have 36 minus 8, which will give us an answer that is 26. Now the last application is the Tower of Hanoi. So the Tower of Hanoi is a mathematical puzzle consisting of 3 rods and n discs. This puzzle consists of some rules. The first rule states that one disc can move only at a time. The second rule is that the disc can only be moved when it is at the uppermost position on the stack. The third one, no disc is allowed to place on the top of the smaller disc. So this is how the Tower of Hanoi works. So first up, what exactly is a linked list? So linked list is a dynamic data structure. It allocates memory dynamically. The nodes are maintained in a non-continuous memory. That is, in linked list we have nodes. So each and every node is connected via a pointer which points to the address of the next node. Each node contains next pointer, that is the next pointer's address, which keeps the reference to the next node, and it also has another section which stores the data. The topmost node always contains null in its address, and this is how a linked list looks like. So this is the top, which is the beginning position of the linked list, and this is the address of the first location, and this is the next node, this is the following node, then this is the last node, and this points back to the head node. So this is how you can implement a stack like data structure using linked list. You can see that we can perform stack like operation, that is the elements are located one above the other and the top is pointing to the head node. Now let us go through the implementation of stack using linked list. First, we will go through traversing of stack using linked list. So displaying each node of the linked list representing stack is termed as traversing. Copy the head pointer to the temporary pointer and then move temporary node through all the nodes and display values of each node. So you can see the animation here will explain you how the traversal goes through the linked list in real time. Now another linked list implementation of stack is the push operation. So adding a new node to the top of the stack is termed as push operation. Generally, in stack we have 3 operations, that is push, pop and peek. So one of the operation is push, where you add an element into the stack. In the same way, using linked list, you can add a new node to the stack and point it as the top of the stack or the first element which represents the top in terms of stack. Now create a node first and allocate a new memory to it. If the list is empty and node consists of data and null is the address, it will be inserted as the first node. If there is some node already existing, then add a new node at the beginning to avoid violations. So the following animation will help you understand how we add a new element or the top element to the stack using linked lists. Now followed by the push operation, we have the pop operation. So now let us go through the pop operation. Removing a node from the top of the stack is termed as pop operation. In the same way, we will be eliminating the first node from the linked list, which is termed as top. Underflow condition may occur when you try to remove the node if the stack is already empty. In stack, node can be removed from one end only. Therefore, the value stored in the head pointer must be deleted and the node must be freed. Followed by the pop operation, we have the peek operation. Retrieving the topmost node of the linked list representing stack without removing the linked list node from the top of the stack is termed as peek operation. Generally, when you're using a stack data structure, just retrieving the value of the top node is called as peek operation. You're not going to eliminate or you're not going to add a new element to the top. You're just going to copy the element or you're just going to retrieve the element which is pointed as top. This operation is called as peek. Now, in the linked list, you can also perform this operation of peek. Now, with the theory discussed, let us execute a practical program based on stack implementation using linked list. Now on my screen you can see a code example using which we will implement stack using a linked list. Now here we have the pop operation, push operation, and top, and then the main function. Don't worry about the code. This particular code snippet will be attached in the description box below, or you can also request us and we will have it sent to your mail ID and you can understand the code and try executing in your local system. Now without further ado, let's directly run the code. So there you go. The code got successfully compiled and we have tried to add some elements into the stack, that is A, B, C. And C is being the topmost element of the stack, and that element has got popped, and followed by that the element on the top currently after C being popped out is B, and the node element B got popped again, and the only element which was present in the stack is A, and that element is also popped out after performing the pop operation, and now currently the stack is empty. You can see that we have tried to push the elements A, B, C, and also we tried to pop the elements A, B, C.
Let's get started with Introduction to Queue. You know that all of us depend on messaging applications like WhatsApp, Facebook Messenger, Instagram chats to communicate with our friends and family members. And while using them, you must have observed that the person you are trying to communicate with receives messages in the same order as you have sent them. Now the question that arises here is, how is this happening? How are these applications maintaining the order of these text messages? And the solution to these questions bring us to queue. Basically, in these applications, a queue is maintained for each user, containing the messages to be delivered to the user. When the user connects to the network, all the text messages in the queue gets delivered, and once the messages are delivered, empty queues get deleted. This example clearly illustrates the importance of data structures. So let's dive further and understand the structure of the queue in depth. But before doing that, let's look at a real-life example of queues to understand it more clearly. The most common and relevant example of a queue is a movie ticket counter. In the movie ticket counter, you must have observed that both of its ends remain open. Also, these ends are fixed with the help of barricades, and that is why no one can enter in between these ticket lines. Additionally, the person who enters first receives a ticket first, and the person who enters last will obviously get served at last. Queues in data structure resembles all these properties of a movie ticket counter, which makes them better at creating virtual first-come, first-served systems. Basically, they are defined as a linear collection of different data types that allow insertion at one end and deletion at another. Unlike any other data structure, the queue ends remain open, allowing it to have different functionalities at both ends. The end at which insertion takes place is called rear, and the end at which deletion takes place is known as front. Furthermore, there are two approaches to consider the structure of the queue, and both of them depend on the approach of the programmer. That means, being a programmer, if you consider the left end as front, then your rear node will be at right end. Otherwise, if you consider the left end as rear, then the right end will be your queue's front node. Unlike arrays and linked lists, elements in the queue cannot be operated from their respective locations. Here, they can only be operated from the front or rear position. Moving on, let's discuss the operations in queue data structures one by one. The first operation is enqueue. It is used to store the elements in the queue. Next up is dequeue. This operation is used for removing them. Further, we have isFull and isNull operations. IsFull function scrutinizes if the queue is full or not, and the isNull operation evaluates if the queue is empty. We also have a peek operation that helps you get the element from the front of the queue without removing it. Let's now understand how these operations work with the help of the following examples. Here we will look at enqueue5, enqueue1, enqueue-2, then isFull, then dequeue, peek, and isNull. But before explaining these operations, it's essential that we initialize the queue data structure by assigning some random size to it. For example, int queue of 3. By this declaration, we are assigning only 3 spaces for insertion in queue. Also, at this phase, there is no element in the queue as it's empty. So both the front node and rear node will point to the same location with null memory space in the storage system. Let's consider that null index to be -1 for ease of our convention. Now the first operation on our list is NQ of 5. As we discussed previously, NQ operation is nothing but the insertion of data into a queue data structure. It begins with checking if the queue is full or not. If the queue is full, then the previously assigned memory is completely filled with data elements. So insertion would not be possible. This is also known as overflow error in terms of programming. But as our queue is empty, so the insertion can be performed here. For that, we have to increment the rare pointer to index 0 from index -1. And once we do that, the data element 5 will be added to the queue. Also for front insertion, both front and rare will point to the same location as there is only one element present in this queue. Let's insert two more elements into this queue with the operations NQ1 and NQ-2. For that, we have to increment the rare pointer to the next index, which will be 1. Now, as the pointer is incremented, so the data will be entered into this position. Next up is NQ-2. Again, we have to follow the same process of incrementing the rare pointer. We will increment the rare pointer to point towards the next index, that is index 2, and hence the data element with value -2 will be entered here. The next operation on our list is full. In this operation, if the rare pointer points to the max size, then the queue is considered to be full as there is no space left for insertion. In our case, the max size of our queue is 12 bytes. Additionally, we are considering to enter only 3 integer elements. And one integer data element takes 4 bytes of the memory space. That means 3 integer elements will take 12 bytes. Hence, this function will prompt queue is full on the screen. Now we will discuss the dequeue operation. If we want to access data from a queue, we have to perform 2 subtasks. The first one is access the data where the front is pointing, and another is to remove the data after access. And this complete process is called as dequeue operation. The first step of this operation is to check if the queue is empty. If the queue is empty, then there is no element available for deletion. This is a case of underflow error. But as our queue is not empty, we can proceed with the next steps. We will be accessing data from the front node, and later we will be incrementing the front pointer in order to remove the link to the previous node so that the data gets removed. Now, front will point to the index 1. Thus, the data value 5 will be removed from the queue and will also be prompted on the screen. Therefore, this function comes with an integer return type. Next up is peek operation. In this operation, element at the front node will be accessed without deleting it. The algorithm for this operation begins with checking if the queue is empty or not. If the queue is not empty, then data at the front node will be accessed with temporary variable and printed on the screen. Advancing further, let's perform 2 more dequeue operations here. First is dequeue of 1 and another one is dequeue of -2. The data at a front node will be accessed primarily, and the front pointer will be incremented to point to the next data element. When we do the pointer incrementation, the link to the previous node gets removed, which results in data deletion. Similarly, we will perform a dequeue of -2 operation here. Now, the front will be pointed to null memory space as there is no element left in our queue, and the data -2 will be removed. The last operation on our list is empty. This function checks if the queue is empty or not. In the previous procedure, we mentioned that if the front points to the null memory space, then the queue is empty. And in our case, the front is already pointing to -1. So the output of this function will be queue is empty. This is all about operations in the queue. I hope that you all are clear with these operations. Next, we will discuss different types of queues and their structures at a glance. Basically, there are 4 types of queues: linear queue, circular queue, priority queue, and double-ended queue. The structure which we have discussed till this time is that of a linear queue, so now we will move on to circular queue. The circular queue is almost similar to the linear queue, except that the last node of this queue is connected to the first. It is also known as ring buffer as all the ends are connected to another end. Additionally, this circular queue is a better version of the linear queue as it removes the drawback of insertion in the linear queue. The empty space available in a circular queue can be filled with the new element by simply incrementing the value of the rare position. We will learn about this in detail in our further sessions. A priority queue is another special type of queue data structure in which each element has some priority assigned with it. Based on the priority of each element, the elements are arranged in a priority queue. If the elements occur with the same priority, then they are served according to the first in, first out principle. In the priority queue, the insertion occurs based on the arrival, while the deletion occurs based on the priority. The above figure shows that the highest priority element comes first, and the elements of the same priority are arranged based on the first in, first out structure. The last type of queue is DQ. DQ is a linear data structure in which the insertion and deletion operations are performed from both the ends. We can say that DQ is a generalized version of the queue. DQ can be used as stack as well as queue, as it allows the insertion and deletion operations on both the ends. If the insertion takes place at one end and deletion at another, then that DQ is known as a linear queue. And if both addition and deletion are performed at a single end, then that DQ is called stack. Advancing further, let's discuss some applications of queues to gauge an insight into the importance of queues. The queue data structure is used in computers, printers, and applications to utilize the benefits of the first come, first served technique. In computers, whenever you work on documents or PPTs, you must have observed that whichever key you press on the keyboard appears in the exact same order on the screen. But when your processor is too busy with other tasks, you might notice that the keys you press appear on the screen with some delay after you press them. Basically, those keys are stored in queue, and when the processor becomes free, it processes in the order the keys are pressed. That means the key pressed first will be written in a Word document first. So this is how computers use a queue to eliminate deadlocks when multiple processes are in a ready state. Next up is printers. A queue data structure is used in printers to maintain the order of pages while printing. That means the pages are stored in a queue in the order that you want to print them, and once the page is removed from an ordered queue, it gets printed. Another most common application of queue data structure is their usage in web or mobile apps. Applications like Domino's, Swiggy uses a queue for maintaining food order status. If you place an order from an online portal, your order ID enters the queue. And once the previous orders before your order ID gets catered, then your order will be catered as well. From these examples, we can clearly say that queues are used whenever there is a need for an FCFS strategy in software development. So whenever you work on projects that need a first come, first serve approach, then remember that you have to implement a queue data structure to complete it successfully. Finally, let's have a look at some key takeaways that we discussed in this session. We started this session by examining the structure of the queue. We learned that the queue is a linear data structure. After that, we talked about different operations of queues, in which we learned NQ and DQ are responsible for data manipulation in a queue. Later, we discussed different types of queues as well. Finally, we discovered some applications of queues and how they fulfill the need of FCFS systems. We have also made it clear that queues can handle multiple data types as well. A queue is a linear collection of different data types that allow insertion at one end and deletion at another. Unlike any other data structure, the queue ends remain open, allowing it to have different functionalities at both ends. Additionally, the queue works with a restriction that insertion should be performed at the rear node and deletion at a front node. Those processes of insertion and deletion are called NQ and DQ respectively. We discovered both of these operations along with three more supportive procedures named as peek, isFull, and isNull. Now that we are considering to implement a queue data structure, so all these operations will become different functional blocks. Additionally, all these operations must take constant time, and it must not depend upon a variable like the number of elements in queue or the size of the queue. By that, what I mean is the complexity of all these operations must be O of 1. Having said that, let's dive deep into the strategy to implement queue data structure. Until now, we have understood that queue is a special kind of list with some restrictions on insertion and deletion. And there are two approaches to deal with queue implementation. The first one is array-based, and another one is linked list based. In this session, we are going to focus on array-based implementation. Initially, let's say we want to create a queue of integer elements. For that purpose, firstly, it is essential to declare an array of random spaces. Let's take 100 as the size of our array. That means our array can have a maximum of 100 integer elements. The declaration of an array is made with this line of code, int q100, where int represents integer data type and q is the name of our array, and 100 is its size. The array that we just initialized is going to store our q. By that, what I mean is at any random index of an array q is going to start with two marked-ends, front and rear. In this array, I'm showing front of the queue towards the left and rear towards the right. For making those end nodes, we need to initialize two pointers, front and rear. At this moment, as our queue is empty, so both of those pointers should point towards -1. So initialization of these pointers should be done as int front is equal to -1 and int rear is equal to -1. When the insertion or deletion happens in queues, these pointers will be either incremented or decremented, so they are an essential part of this queue implementation process. Now you must be clear with the array and pointers declaration part, so let's dive further and formulate code for queue implementation using a one-dimensional array in C++. It is essential to include header files into our source file as we cannot access standard C++ functionalities without them. That is why here we are going to load IOStream and standard input-output files along with using namespace std. Once this is done, we will initialize our array along with front and rear pointers. Remember, we always have to declare the size of an array before compilation. That means we cannot update the size of an array at runtime. This scenario is the biggest limitation of queue implementation using arrays. Having said that, let's proceed with pointers declaration. Now we are done with the initialization process. We will now work on implementation of queue functionalities. Let's first work out supportive queue functions like isNull, isFull, and peek. isNull function validates if the queue is empty. And as per our previous discussion, when both front and rear points to -1, then the queue is considered to be empty. So the condition to determine if queue is empty will be if rear is equal to -1 and front is equal to -1, it will return queue is empty. If the queue does not satisfy the previous condition, then it is not empty. So by using the else condition, we can display the queue is not empty. Next up is isFull function. This function validates if the queue is full, and we can clearly say that if the rear pointer is equal to the max size of the queue, then our queue is going to be completely full. Next is peek. The peek function extracts the element where the front pointer is pointing without removing it from the queue. For this functionality to work, our queue must contain data elements in it. What I mean is our queue should not be empty. If our queue is not empty, then data at the front node can be accessed. This is how we implement supportive queue functions. Let's immediately dive into the development of main queue operations, enqueue and dequeue. For enqueue operation, if the queue is full, then our function should prompt an overflow error. For that to happen, we have to put this condition. If the front pointer is pointing to -1, then we have to increment the front pointer to 0 manually. Otherwise, it can be incremented by rar ++. After pointer incrementation, we have to ask for a data element to enter into the queue. Once the data is given, it should be inserted at the position where the rar is pointing now. Finally, let's code the final main queue operation called as dequeue. If the queue is empty, then there is no element for deletion, so it should prompt an underflow error on screen. Also, if there is only one element left inside queue, then both pointers should again be pointed towards -1. For that, let's write another condition here. If both the previously mentioned conditions are false, then deletion of an element can be achieved by just pointer incrementation. We have implemented all the queue functionalities here, but we haven't implemented a function that can show us how our queue looks. So for that, let's implement one more function with the name display. This function should prompt the elements of the queue on the screen. Elements will only be printed if the queue is not empty. Hence, we have to check for the emptiness of the queue first. Finally, we are done with the hard part. So let's arrive at the main function to contemplate these operations in order to visualize outputs. We are going to use a switch case to take a user command. Thus, not to waste your time on this, let me just get done with this block ASAP. That's all, we are done with the queue implementation using arrays. Let's just examine if our code works fine or not by compiling it. This program should return a console that asks the user to give commands for performing different operations. So as you can see on your screens, if I input 1, I can perform insertion in a queue. Let's perform some insertions now. We will insert 4 elements, first 3. Then 21, next 78, and finally 12. After inserting these elements, we will print the state of the queue using case 3. Now let's also check the dequeue function. If we perform a dequeue operation, then 3 should be removed from the queue. Let's check if it is removed using the display function. And yes, our code works just fine. Now if you're concerned about this code, then don't be, as we can send it over to you if you drop your email IDs in the comment section below. Additionally, you can also try to run it on your local system to have a better understanding of the concept.
Introduction to priority queue. Primarily, we will have a look at the real-life example of priority queue to understand it better. A hospital emergency queue is almost an ideal example of priority queue. When you go to the hospital, you must have observed that the person who needs immediate medical attention will be treated first, irrespective of his arrival at the reception. That means treating a person who is in agonizing pain or in emergency medical condition is the priority of the queue of patients. Priority queue in computer science also works with same approach. So what exactly is this priority queue? Well, a priority queue is an abstract data type that operates similar to the normal queue, except for the fact every element has certain priority assigned to it. This definition of priority queue suggests that this particular type of queue also follows the same restrictions for insertion and deletion of data elements. The insertion in the priority queue will only be achieved at one end and deletion at another or opposite end. Additionally, the priority of data elements will determine the order of removal. The elements which has higher priority will leave the queue at first, and the elements which has lower priority will definitely leave the queue at last. As a side note, I would like to tell you guys that the priority queue only supports the elements that are comparable, meaning the data that we are going to insert into priority queue must be orderable. The compiler should not be facing any difficulty while comparing these data elements. Otherwise, the execution of a priority queue will definitely fail. Moving ahead, let's have a look at an example of priority queue. In this priority queue, we will insert 7, 2, 45, 23 and 12 respectively. These elements are not ordered. So how the priority queue is going to store them in order? Well, at the time of insertion, the priority queue conducts a comparison of each element with every other element present inside a queue to store them in order. But as there is no element inside a queue, so the first insertion, that is an element with value 7, will be attained. Followed by that, the next element will be inserted in a queue. Since the newly inserted element is smaller than that of previously inserted element, will swap their positions in order to maintain order. Remember, the element with least value will have a higher order and the element with greatest value will have a least priority or order. Now we will insert the next element in a queue, that is 45. As 45 is a larger element than the elements inside the queue, there is no need to shuffle elements. When we make the next insertion, the element 32 will get inserted at index 3. Now this element is smaller than that of 45, so the algorithm will have to swap the locations of these elements. Now we will perform the final insertion into our queue. We will insert 12 at index 4 now. But as you can see, this element is smaller than both the previous elements. Thus the algorithm will have to swap their positions. Now 45 will reach the end of queue as it is the element with highest value, and 2 will remain at the front of queue as it is the least valued element. As a humans, we could see the numbers visually inside the priority queue, and further, we can easily arrange them. But how does the machine know this? Does it restore all the elements inside the priority queue before each insertion? No. Obviously, that would be highly ineffective as there will be n comparisons for insertion of n elements, leading to time complexity big O of n square. This is an enormous time complexity which we cannot allow in any software application. We will understand how the priority queue manages to reduce this time complexity in upcoming topics. But right now we will contemplate different properties of a priority queue that we have learned from previous example. The first property of priority queue suggests that each element has a certain priority assigned to it. That priority might depend on value of data element. It can be either larger or smaller. The next property states that element with higher priority will leave the queue at first, where the element with least priority will leave the priority queue at last. Further, if two elements have the same priority, then the element will be removed from the priority queue based on their arrival. That means the element which arrived at first out of the elements having same priority will be removed first. Now, moving ahead, we'll deal with the representation of priority queue using a linked list, as usage of arrays is not an ideal way to implement priority queue. If we consider array implementation of priority queue, then inserting items into the sorted array will cost us big O of n. And in general, processing each element will further cost us big O of n square as discussed previously. So in this tutorial, we'll just look into the linked list representation of priority queue. We will understand the representation of priority queue with the help of an example. Initially, let's say there are 3 elements inside a linked priority queue and all of them are in order. 3 being the least element has highest priority, where 43 has the least priority. The purpose of keeping 3 at the head node is that we want our priority queue to delete elements according to their priority. Now, we want to insert a new node consisting of data element 2. And as the data element is smaller than the element at head node, that is 3, so this new node should be inserted prior to it. This particular scenario of insertion seems pretty perfect as it does not cost us more time. But what if the element is significantly larger than all the nodes in queue? For instance, let's say we want to insert 45 as a new element. In that case, primarily it will be compared with element 2, and as 45 is larger than 2, our temporary pointer will move to the next node for comparison. Now, 45 will be compared with element 3, and again, the temporary pointer will be moved to the next node for comparison. After 2 comparisons, the temporary pointer has reached element 17 for performing the next comparison. And here also, 45 is larger than 17, so the temporary pointer will again move towards the next node. Now finally, our temporary pointer has arrived at the tail node consisting of element 43. Again, in this case, the element 45 is larger than 43, thus the new node will be inserted after node containing data element 43. From this specific example of insertion into a priority queue, we can clearly see that there are n comparisons leading to the time complexity big O of n, where the complexity of deletion remains constant, that is big O of 1. While understanding the representation of priority queue, we came across some facts that make priority queue implementation using linked list quite vulnerable. So here we will again try to recall them. The first drawback of priority queue implementation using linked list is that it costs us big of n for inserting a new element. Further, it also costs us big of n for peak operation. And as memory and time management is the purpose of data structure, hence we must try to analyze other implementation strategies. That is why in upcoming slides we'll look into different approaches to implement a priority queue. There are three approaches that implement a priority queue with complexity less than big O n square. We have already discussed the linked list, so let's also look into other two approaches. Binary heap and binary tree provides almost similar complexity. These approaches cost us big O log n for insertion and deletion, and big O 1 for peak operation. But which one of these operations is most optimal approach to implement priority queue? Well, to answer this question, we again need to discuss about memory management in the case of both these data structure. You guys know that binary heap data structure is implemented using arrays. And since it utilizes arrays, there is always a better locality of reference as well as operations become more cache friendly. The binary search tree uses pointer to implement front and rear node, which definitely takes up more space in memory. Due to that, building a self-balancing BST cost us big O of n log n, where binary heap just cost us big O of n. These facts clarify that the binary heap is the best data structure to implement a priority queue. Now you must be thinking about what exactly the heap is and how does it work. So moving forward, we'll look into the definition of heap and its properties. Basically, a heap is a tree-based data structure that satisfies the heap invariant, or in simpler words, heap property. The heap invariant states that if A is a parent node of B, then A is ordered with respect to B for all nodes A and B in heap. What that means is the value of parent node is always greater than or equal to the value of child node in the heap, or other way around, the value of parent node is less than or equal to the value of child node for all nodes in a heap. Further, there are two types of heap named as max heap and minimum heap. First, we will look into max heap. The max heap is heap in which value of parent node is greater than the value of child node. For this particular example of max heap, you can see that the root node is the biggest element in tree and each child node is smaller than its parent node. The next type of heap is minimum heap. The min heap is heap in which the value of parent node is less than the value of child node. In this specific example, you can observe that each child node is larger than its parent node and the element at the root node is smallest element of the heap. Both the structures that we have discussed are binary heaps as every node has only two children. In upcoming slides, we will discuss some complex structures of heap data structure to better understand how we can judge if a tree-like structure is heap or not.
Okay, so you can see a tree-like structure on your screen and we are supposed to check whether if it is a valid heap data structure or not. But actually here I would like you all to give it a try by yourselves. You can also pause this video if you want, but here I will provide you with a short moment to inspect this structure. Alright, I can clearly say that this is not a valid heap data structure. As you can observe, the highlighted part is violating the heap invariant. Moving forward, let's analyze another tree-like data structure to consider if it is a valid heap or not. Well, yes, this is a valid heap because even though this one is strangely structured, we are free to move around the visual representation of nodes to make it organized. Now you all must be thinking how we can do that. Well, we'll understand that scenario in upcoming slides. Now, how about this one? Is this a valid heap? No, right? This is not a valid heap. This structure is not even a tree as it forms a closed cycle and every heap must be a tree. So it's pretty clear that this is not a valid heap. Now, what about this one? Is this a valid heap? Yes, this is a valid heap as it satisfies the heap invariant that all the child nodes must be greater than or equal to or smaller than or equal to its parent node. Now, this is the last structure that we are going to check if it is a valid heap or not. What you guys think? Is this a valid heap? Well, I think it's pretty clear that this is not a valid heap, but it can be converted into a heap by making a one small change. Now, if we make 6 as our root node, then this structure will get converted into a max heap, which is absolutely a valid heap. I hope you all are clear with the heap invariant and how to judge if a given tree is a valid heap or not. Now moving ahead, we'll discuss the different types of priority queue. Basically, there are two types of priority queue based on the priority of elements. If the element with smallest value has highest priority, then that priority queue is called as min priority queue. And if element with higher value has the highest priority, then that priority queue is known as max priority queue. Furthermore, it's vividly clear that the min priority queue can be implemented with a minimum heap, where the max priority queue can be implemented using maximum heap. Moving ahead, we'll deal with the operations in priority queue considering the heap as implementation strategy. The common operations that we can perform on priority queue are insertion, deletion, and peak. But there is one more hidden additional operation that gets performed during these operations. That operation is called as heapify. Heapify manages the priority of data elements in a heap by shuffling the data elements after new insertion or deletion. First of all, we will understand how insertion in priority queue happens with the help of an example. In this example, we are inserting a new data element that is 43. But due to this insertion, the structure disobeys the priority queue invariant that the parent node of the max priority queue must be greater than its child node. Now, the heapify operation solves this problem by rearranging data elements by carrying out the comparison. In this particular case, 43 becomes the parent node where 40 becomes the child node. The next up is deletion. As we know, the highest priority element will be the first to leave the priority queue, and further, it is stored at the root node of a max heap. So definitely, the element present at the root node will get removed. But due to this operation, the order of priority queue gets affected. However, the heapify operation comes to the rescue. It reshuffles the elements of the priority queue to rearrange them in order. The next operation that we are going to discover is peak. The peak operation simply returns the element present at root node without removing it, and it is easily accessible. Thus, the time complexity of this operation is big of 1. I hope you all are clear with the operations that can be performed on priority queue. Moving forward, we'll try to implement them with the help of minimum heap. As discussed earlier, while implementing a heap data structure, we know that all the elements will get stored in an array, and we don't have any pointers pointing to either child or parent nodes. So how exactly does the heap data structure remember nodes like parent nodes and its left or right nodes? Well, if you have learned binary trees, then you must know the formulas present on your screen. These formulas determines the left child, right child, or even the parent node of any binary tree. Let's understand how this phenomenon works with the help of an example. We'll begin with index 0. If we enter 0 in this arithmetic expression, then we will get 1 and 2 as output. That means the element at index 1 will be the left child and element at index 2 will be the right child. And tree structure will look like this. Now, Moving ahead, let's take an example of index 1. For index 1, the left child will be at index 3 and the right child will be at index 4. Similarly, for index 2, the left child will be at index 5, where the right child will be at index 6. Using these formulas, we'll be implementing heapify and primary queue operations. So note them down for further reference. Now moving further, we will visit code editor to implement priority queue data structure using C programming language. Previously, I mentioned that heap is implemented using arrays. So, to begin with heap implementation, primarily we will create a structure consisting of different variables or objects needed to implement heap data structure. So, let's create a structure, struct heap consist int size, int count variable, and int star heap array, which is a dynamic array that we are creating here. And next, we'll also declare a pointer to heap structure along with size and count variable in a global scope. So let's do that. Int star heap comma size comma count. We'll create one more variable, int initial underscore size, to represent the initial size of our priority queue, and let's assign it value 4 for now. Okay. Now it's time to allocate memory to our heap array. For this purpose, we'll create a new function called heap underscore init. So let's create this function, void heap underscore init, and inside it we'll pass an argument struct heap star h, which is a reference of this structure that we created previously. Okay. In this function, let's initialize the variables that we have created inside this heap structure. So for that, we'll initialize h arrow operator count is equal to 0. Similarly, h arrow operator size is equal to initial underscore size, and h array is equal to int star malloc size of int star 4. This statement is just allocating 4 integer variables to our heap array. Basically, our heap array is dynamic data structure. That's why we have to provide it with dynamic memory using malloc. If you are using C++ programming language to implement this data structure, then you can use new instead of malloc. Moving forward, now we'll work on our condition if not h arrow operator allocates memory to heap array, then printf error while allocating the memory, and that /n Next, we will write exit command. Okay. With this, we have successfully implemented our heap init function. Now moving ahead, let's implement heapify function to move the nodes. For that, we'll create a heapify function void max underscore heapify int star data int log int count. So all these are required variables to implement this heapify function that we have passed in argument for this max heapify function. Now let's create few more variables that we need. Int left comma right comma largest comma temp. Now as discussed earlier, left will be equal to 2 star location in array plus 1, and right will be equal to left plus 1. Now let's say largest is equal to LOC, and we'll work on conditions now. If left is greater than or equal to count, and data left is greater than data largest, that is the location we have stored in largest variable, then largest is equal to left. With this block, what we are doing is we are checking if the element at location left is greater than the element at recent position, and the value at left is also greater than the value of recent location. If these conditions are true, then we will set the recent location as left. And here we are getting signal that there is semicolon missing over here, so we'll add it. Okay, now let's work on next condition. Now we will check the value at right position. If the recent location is greater than the right and the value at right is greater than the largest value, then element at largest will be set to right. So for that, we'll write condition if right is greater count and data right is greater than data largest, then largest is equal to right. Otherwise, if largest is not equal to location, then we will store the data present at location in temporary variable, and data LOC is equal to data largest. This is a swapping operation that we are carrying out here. And next, data largest is equal to 10. And now we'll make recursive call to our heapify function max underscore heapify data comma largest comma count. With this, we have successfully completed our heapify function. Now we will work on insertion operation on priority queue. Let's call this function heap underscore push because we are treating this structure as heap, right? So in heap, insertion is called as push operation. So we'll call it void heap underscore push and we'll pass arguments struct heap star h int value. And inside this function we'll create few more variables int index and parent. If you guys remember, the initial size that we have allocated to our array is 16 bytes. You can verify with this statement here that we are providing 16 byte size to our heap array. But what if you want to insert elements more than 4? Then what we'll do? Well, for that, we'll need to increase the size of our heap array. So we'll do that here. For this resize, we'll create if condition if h dot count is equal to h dot size, then h dot size plus equal to 1 and h dot heap array is equal to realloc h dot heap array size of int star h dot size. Basically, we are using realloc function in C to extend the dynamic memory space for our heap array. And in order to increase the size, we have to increment the size variable first. So that's what we have done in this statement here. And now, once done with this, we'll check if our dynamic memory is getting allocated or not. So for that, we'll add one more if condition inside this if block. So it can be called as nested if you guys want. Dot heap array, then exit -1. Now we'll move out of this if block and we will set index variable to h dot count plus plus. Basically, we are iterating with help of index variable here. So next we'll add for condition, for loop, index to index is equal to parent. And inside this condition, we'll make parent node is equal to index -1 by 2. This is nothing but the formula that we have discussed in previous part. Now we'll add one more condition inside this for loop. If h dot heap array parent is greater than or equal to value, then we will break this for loop. Otherwise, h dot heap array index will be equal to h dot heap array parent. Now we'll move outside this for loop and we'll add one more condition of insertion, that is h dot heap array, and at position index we will add the value provided by user using argument to heap push function. Okay, with this we have successfully created our heap push function. Now we'll move towards the next function, that is heap underscore delete. For that we'll create new function heap underscore delete, and let's make this function integer, and we'll pass struct heap star h as an argument. We will create one more variable temp is equal to h arrow operator heap array, and inside this we'll pass a negating index. That means we are using this temporary variable to traverse through all list of elements. So for that we'll write dot dot minus minus h arrow operator count, which will decrease count one by one. Now next we'll add condition if h arrow operator count is greater than or equal to h arrow operator size plus 2 and h arrow operator size is also greater than the initial underscore size. Okay. Then what we will do is we will set size to negate itself by 1 for each iteration, and then we will add h arrow operator heap array is equal to realloc h dot heap array, comma, size of int star h arrow operator and size. Size. And semicolon. So basically what we are doing here is we are checking if count is smaller than the size of heap plus 2 and the dynamic size of queue is also larger than initialized size, that is 4, then what we are doing is we are reducing the size for deleting an element using this statement, and in next statement we are reallocating that deleted space. So this is how this if block works. Now moving forward, we'll add a condition to check if memory is getting reallocated or not. For that, we'll write condition if not h arrow operator heap array. Then what we'll do is exit with -1. Okay, now let's move out of this if block, and now we will set this removed variable to h arrow operator heap array and index 0. So if you guys remember, 0 is the index of the highest element in our maximum heap. What I mean here is the element with highest value is stored at index 0 for max heap. Now moving forward, to delete this element, what we'll do is we will set h dot heap array and index 0 is equal to temporary variable or pointer that we have created previously, and next what we'll do is we'll call max underscore hippify function to rearrange the structure of our priority queue which has been shuffled due to this delete operation. Now for that we'll pass arguments our heap structure, that is heap array, and next the index which was removed and the count variable, and we'll return the removed element. Okay, with this we have successfully implemented our delete function. Now to understand the order of deletion in priority queue, we will implement one more function called as mtpq. So let's create this function. And in this function we'll pass the reference of heap structure in order to operate on it. So let's pass the structure heap star h, and inside this function we will create a while loop h dot count is not equal to 0, then printf modulus D and recursive call to heap delete function in which we'll pass h. Now we are done with this empty function. Further, we'll create one more function to visualize our priority queue. Let's call this function void heap underscore display, and inside this we'll pass structure heap star h. And now we will create one iterator element, and using that iterator element we'll create for loop I is equal to 0 to I is greater than arrow operator count plus plus I. And inside this for loop we will print the elements present in our queue using this format modulus D, and we'll call heap array. But for that we'll need to call structure as well. Heap array, and we'll pass this iterator variable into it. Okay, and then next we'll get outside this for loop and we'll printf this to the next line using /n. Okay, now we have implemented all the required function for our priority queue. Moving forward, we'll work on our driver function, that is main method, to contemplate the result of our program. So for that we'll first call struct heap h, then we'll call init function to create heap structure, so heap init, and we'll pass the address of h. Next we will call heap underscore push function to insert element and h comma 1. Next I'll copy this part, we'll paste it to insert another element. Now we'll insert 5 here. Next paste, and we'll pass 3. Next we'll insert element 7. Next we'll insert element 9, and after this we'll insert element 8. Okay, so now let's display the elements inside our heap using heap underscore display function, and let's pass and h object to print it, and again we'll call empty pq function, empty pq, we'll pass h, and after deleting all elements it will return the state of our heap array again, or our priority queue. So finally we'll add return 0 statement, and now our code is ready. So let's compile it and check it if it works fine or not. So we are getting 4 errors here, guys, so we'll need to resolve them. First we'll need to check line number 82. So for 82, okay, here we haven't added semicolon, so I think this should be fine now. Still we have 2 errors. before I reach there. So let's recompile it and check it if it is working fine now. So we have received our output now. Now if you look at our output is printing elements 9, 7, 8, 1, 5 and 3. And deletion of elements is also happening according to their order. So 9 is getting deleted first after 8, 7, 5, 3 and 1. So that means our elements are getting removed in proper order. Further, we can say that our program for priority queue implementation works fine. Now, if you guys are worried about this program, then not to worry. We have you covered. You can mention your email IDs in comment box below and we will send it over to you.
So how does algorithm work in real life? So we'll have a use case here. On my screen, we have a lady and she is Shreya. Shreya wants to make some tea and for that she is following some steps. So the first step is she'll take a pan and fill it with water and place it on a gas stove. Followed by that, the second step is she'll make sure that the water comes to a nice boil and then she adds some tea leaves and sugar. Followed by step 2, we have step 3 where she'll allow the leaf to be fully expanded and she'll add some milk after that. Next we have the step 4 where she will wait for the tea to come for a good decent boil. Next we have step 5 where she'll turn off the gas and she'll take the pan off from the stove and the tea is ready to get filtered. And lastly we have the step 6 where she is all set with the tea. So in computer science, an algorithm is a method or set of rules that we must be following to perform some specific calculations or other problem-solving operations. As a result, an algorithm is a collection of rules or instructions that govern how a work needs to be conducted step by step to achieve the desired results. To accomplish a task, we first provide some input and then follow a sequence of steps to acquire the required outcome of the input. So that is the fundamental definition of an algorithm, and we also had a use case. And now we will move ahead and understand the characteristics of algorithms. So basically we have 6 characteristics of algorithm. So the first one is it should be clear and unambiguous. The second one is that it has to be well-defined inputs. And the third one is that it has to be having well-defined outputs as well. The fourth property of an algorithm is its feasibility. Followed by that, finiteness, and finally we have language independence. Now, we will look into each one of the characteristics in detail. So first we have clear and unambiguous. So this statement is the one which states that the algorithm should be straightforward, simple, and easily readable. Each one of its steps should be distinct in every way and lead it to a single conclusion. So the next one is it should be having well-defined inputs. So this means that an algorithm should indicate what output can be expected as well as the input should be properly well-defined. Now we have the third one. Similarly, we should also have well-defined outputs. So the well-defined output characteristics of an algorithm means that the algorithm must clearly indicate what output can be expected as well as the output should also be well-defined. Followed by the third characteristic, we have the fourth characteristic, that is the finiteness of algorithm. So the finiteness of algorithm says that the algorithm must be finite and it must not result in infinite loops or similar situations. So followed by the fourth one, we have the fifth characteristic that defines about the feasibility of an algorithm. So feasibility of an algorithm states that the algorithm must be really simple, generic, and practical. It must be able to be executed with resources available. Now, the last characteristic of the algorithm is being independent of the language. So it means that the algorithm should be defined in such a way that it is completely independent of the language. It must be simple instructions that can be implemented using any programming language. So these were the 6 major characteristics of algorithm. Now let's move ahead and understand How to write an algorithm. Writing an algorithm does not have any hard and fast rules. Next, algorithms are never created to support a specific programming language. As we all know, algorithms should be capable enough to support the conditional statements such as if else, switch, etc. An algorithm should be capable enough to execute some of the conditional statements such as if else, switch, etc. And also it must be capable to execute the iterative statements such as for loop, while loop, do while loop, etc. We usually create algorithms in a step-by-step manner. However, this isn't always the case. After the problem domain has been well defined, algorithm writing is a procedure that is carried out. We build an algorithm to find a solution to a problem. A problem can be resolved in a variety of ways. Let's look at an example of how to write an algorithm. Consider the following scenario. We need to create an algorithm to determine the largest number among the three given numbers x, y, and z. As a result, the initial solution to the problem can be written in this manner. So we begin with reading all the three numbers, and in the second step we will have a condition that says if x is greater than y, we will proceed to step 4, else we will proceed to step 5. Next, in step 4, we establish a condition that if x is greater than z, then x is the largest of the three numbers. Otherwise, z is the largest. If y is greater than z, z will be the greatest number. Otherwise, y will be the largest number amongst all the three in step 5. And the procedure will be terminated. Let's have a look at what the next solution has to offer. In this algorithm, we begin by reading all the three variables, then compare all the three numbers in the third step to determine the largest number, which is if x is greater than y, then there is another if else statement that states that if x is greater than y, then x is largest. Otherwise, z is the largest. Then there's if else statement which says that if y is greater than z, then y is greater. Otherwise, z is the greatest of the three numbers. So this is how we have multiple solutions to the same problem. So after discussing these solutions, we will move ahead and understand algorithm analysis. The algorithm may be studied in two levels. First, before it is made, and then after it is created. The two analyses of an algorithm are as follows. The first one is priori analysis and the second one is the post analysis. So first we will talk about the priori analysis. Priori analysis refers to the theoretical analysis of an algorithm performed before its implementation. Before implementing the algorithm, other parameters such as processor speed might be considered, which does not affect the implementation component. Next, we will talk about post analysis. A practical analysis of an algorithm is called as posterior analysis, and it utilizes any computer language to build the algorithm. The purpose of this analysis is to determine how much time and space the algorithm takes to operate. Now, after being understood the algorithm analysis, we will be able to comprehend the algorithm complexity. Two methods can be used to assess the algorithm complexity. The first one is time complexity, which states that the amount of time required to finish an algorithm's execution is known as its time complexity. Followed by time complexity, the other one is the space complexity, which is calculated by the quantity of space required to solve a problem and produce an output of space complexity of an algorithm. Let's take a closer look at these complexities. Now we will begin with time complexity of an algorithm. The big O notation is used to express an algorithm's time complexity. The asymptomatic notation is used to depict temporal complexity of big O notation. The time complexity is mainly determined by counting the number of steps required to complete the task. Let's take a look at an example to understand this time complexity in a much better way. If we want to find out a multiplication of n numbers, we can do it by executing a loop from 1 to n, then calculating multiplication when the loop ends. Then multiplication holds the n numbers multiplication, and last we return the calculated multiplication. The loop statement's time complexity will be at least n, and when the number of n increases, the time complexity will also increase. While the code's complexity, that is, returns multiplication, will remain constant because its value is unaffected by the value of n, and it will obtain the result in every single step. Next, we will discuss about space complexity, which is expressed with big O notation, just as time complexity. These 4 items are stored in space complexity. It initially saves program instructions, then stores constant values, then stores variable values, and finally it keeps track of function cells, jumping statements, and so on. The sum of auxiliary space and input size is used to calculate space complexity. The extra space or temporary space used by an algorithm is referred to an auxiliary space. After learning about algorithm complexity, we will look at some of the algorithm's pros and cons. So let's start with the advantages of algorithms. Firstly, algorithms are easy to understand. Next, algorithms are step-by-step representation of a solution. And lastly, the problem is broken down into smaller bits or steps in an algorithm, making it easier for the programmer. Now, an algorithm also have various drawbacks, one of which being it takes long time to write, hence it is time consuming. Second con of the algorithm is algorithms make it harder to demonstrate branching and looping statements. So followed by the advantages and disadvantages of algorithms, we now enter into the final segment where we discuss the differences between algorithms and programming. So the first difference is that an algorithm is a type of programming. On the other hand, a program is more directly associated with the computer performing one or more tasks, but an algorithm is more of a notation, a technique for solving a problem. Now, let us discuss the second difference. An algorithm can be decoded or run by a human, whereas the program is only run or decoded by a set of compilers of the computer. Now, the third difference. Basically, an algorithm is a design of the solution to the problem. Here, we can only analyze the solution, but we can never run it. But whereas on the other hand, programming is completely a different ball game. Here, you can directly implement a certain phase or an entire program and test the programs and get an output. So the fourth and the last difference between an algorithm and programming is an algorithm is written using natural human vocabulary, whereas programs are written using any programming language such as C, C++, Java, Python, etc.
Well, recursion is a process in which a function repeatedly calls itself either directly or indirectly. Those calls are majorly done by explicitly calling function by its name. However, it can also be accomplished by implicit calling as well. The fundamental idea behind calling the function over and over again is to break a larger problem into smaller subproblems. We do this for reducing the computational complexity of a larger problem by breaking it into several pieces. This tactic is also called as divide and conquer approach in programming. So now you must be thinking about how we can break the larger problem into smaller subproblems. Well, to do that, we break the given problem statement into two parts. The first one is base case and the second one is recursive step. The base case is nothing but the simplest instance of a problem that consists of condition which holds the recursive function. Given the function call's argument, this base case computes the output of our program right away. Whereas in the recursive step, we compute the result using one or more recursive calls to the same function, but with the inputs decrease in size or complexity. To understand this breakdown, let's have a look at mathematical aspect of recursion. Suppose you have to formulate a mathematical function for computing the sum of n natural numbers. That means the function that you are going to create must calculate the summation of all natural numbers in the range 0 to n. Mathematically, it can be represented as summation of all numbers from k is equal to 0 to k is equal to n. Now the critical question here is, how can we actually represent this in form of recursive function? The answer is quite simple. All we need to do is break this larger problem into small fragments. We can represent this problem as n plus sum of all natural numbers till n minus 1. This process of traversing in function f n minus 1 times is called the recursive step of our problem statement. Whereas the base case is a condition which is stopping the recursion when k is reaching value 0. In terms of programming, it can be represented using if block. Now I hope you guys have understood how we can break a larger problem into smaller subproblems. Moving further, we are going to understand how recursion gets executed in memory area. In order to do that, we'll take this C program as an example. In this program, we have two methods. The main method contains one variable and the statement that invokes a function named fun. This function fun is making a recursive call in its function body. We have both base case and recursive step inside this function's body. Now, whenever a function is called, its activation record will be maintained inside the stack. So, for this program, we are going to look into its control flow. As we know, the main function gets invoked primarily by an operating system. Thus, we'll include the main function at first in our memory stack. This activation record will consist of local variables of function, parameters, and the record of return address to the caller. But here, for the sake of simplicity, we are just maintaining the local variables inside the activation record. After this step, as you can see, the main function is activating method fun with argument 3. Once activated, it will prompt 3 on screen and will invoke fun 3 minus 1, that is fun 2. Now again, as 2 is greater than 0, the control will invoke fun 2 minus 1, that is fun 1. After this, the control will activate fun 0. This time, once the control enters an if block, it will execute a return statement, and activation record 0 will get popped out of the memory stack. Further, every function inside the memory stack will get popped out from it, which will result in generation of output. The output that will get printed on the console for this particular program is 321. Now, here is the interesting question that we want you all to answer. Based on the properties of recursion that we have discussed till now, which of the following statements seems right to you? The options that we have are: recursion is always better than iteration. Option B. Recursion uses more memory compared to the iteration. Option C. Recursion uses less memory compared to the iteration. It will be interesting to see how many of you guys will get this right. So guys, do leave your answers to this question in comment section below. In a week's time, we'll be announcing the right answer and you all can check it out. Now moving ahead, we'll discuss different types of recursion in programming. There are basically 4 types of recursion. The first one is direct recursion, the second one is indirect recursion, the third one is tail recursion, and the fourth one is non-tail recursion. So let's discuss direct recursion. A function is called direct recursive if it calls itself in its function body over and over again. To better understand this definition, let's look at the structure of a program that is direct recursive in nature. In this program, we have a method named fun which is calling itself again and again in its function body. Thus, we can say that it is direct recursive in nature. Next up is indirect recursion. The recursion in which the function calls itself via another function is called as indirect recursion. For example, in this program, you can clearly see that the function fun1 is explicitly calling fun2, which is invoking fun1 again explicitly. Hence, we can say that this is an example of indirect recursion. Further, we have tail recursion. A recursive function is said to be tail recursive if the recursive call is the last execution done by the function. Let's try to understand this definition with the help of an example. If you observe this program, you can see that the last line ADI will execute for method fun is recursive call, and because of that, there is no need to remember any previous state of our program. Finally, we have a non-tail recursive function on our list. A recursive function is said to be non-tail recursive if the recursion call is not the last thing done by the function. After returning back, there is something left to evaluate. Let's consider one example. In this function, you can clearly observe that there is another operation after the recursive call. Hence, our ADI will have to memorize the previous state inside this memory block. That is why this program can be considered as non-tail recursive. Now finally, let's implement a program to demonstrate the recursion. The program that we are going to implement is solution to the problem statement that we discussed earlier. According to that problem statement, we have to calculate the sum of n natural numbers given the number n. Now, in order to address this problem, we are going to use C programming language. So without any further ado, let's head over to the code editor. Now, in order to get started with coding implementation, first we'll create an utility function to calculate sum of n natural numbers. So let's do that, and we'll pass an argument int n. Now we have arrived inside the body of function sum. What we'll first do is we'll calculate sum of n minus 1 natural numbers by making a recursive call to function sum. So let's do that, sum n minus 1, and we'll store this value inside a temporary variable. Now we'll add this temporary variable's value to n in order to return it as a result. The statements that we just wrote are called as recursive steps. But if you observe this statement, we are not putting any limitation to our recursive call. So that is why we'll have to add base case to our function. So let's do that. If n equal to 0, then return 0. With this, we have successfully implemented our sum function. So let's work on our driver method to generate the result. In this driver method, first we'll create a variable n, and after that we'll write a printf statement. Enter the natural number n to calculate the sum of n numbers. Semicolon, and in next line we'll write scanf statement in order to take input from our user. So inside this we'll write modulus d, comma, ampersand n, and semicolon. And in next statement we'll make a call to our sum function in order to calculate sum of n natural numbers. So how we can do that? Well, we can add modulus d here, comma, sum n, semicolon, and I hope our code works fine now. So let's check it by compiling. Here the console is asking us to provide with value of variable n, and I'm going to provide value 5 here. So let's provide value 5 and enter. So the output that we are getting is 15 here. That means our code works fine. Now let's get started with our first topic. What is DQ? DQ is an abbreviation for double-ended queue, and as the term double-ended queue suggests, it is a type of queue with some advanced features at both of its ends. But previously, we have learned that the basic queue data structure must perform insertion from one of its end and deletion from another or opposite end. So what new limitation or feature does this particular type of queue brings? Well, the DQ extends the concept of a linear queue by implementing insertion and deletion at both of its nodes. By that, what I mean is the DQ data structure is acquainted with the possibility to insert and delete new elements at any node. That is why DQ is concerned as more generalized version of queue data structure. Now, moving ahead, we shall understand the key properties of DQ. The first property of DQ states that the DQ can use the LIFO principle for inserting or removing elements. The last in first out principle is used while implementing stack data structure, and according to this principle, the queue elements must be inserted from one end and should also be removed from the same end. For instance, we are storing some elements inside this queue structure which is performing both insertion and deletion from one end. However, when deletion begins, the element inserted at last will be removed first, whereas the element stored at first will get removed at the end. This property clears that the DQ can inherit all the properties of stack data structure. The next property of DQ states that the DQ can use the FIFO principle for performing both insertion and deletion operations. That means the element which enters inside the queue at beginning will also leave the queue at first. Further, the element which entered at last can leave the queue at last. Both of these properties displays the uniqueness of this particular type of queue data structure. Now in upcoming slides, we will understand different types of the DQ. The first type of DQ we have is termed as input restricted queue. This terminology itself suggests that this particular type of DQ will have some restrictions while performing NQ or insertion operation. In this type of DQ, the insertion can only be performed from one end, where deletion can be performed at both of its ends. The representation of DQ shown below explains how the operations in this type of DQ will get accomplished. The next type of DQ is output restricted DQ. This term makes clear that this type of queue will have some restrictions while performing deletion operations. In this specific type of queue, the removal of elements can only be performed from one end, where the insertion can be performed at both of its ends. This particular structure of a queue explains how the different operations will take place in this type of DQ. Now here is the interesting question that we want you all to answer. Based on the properties of DQ that we have discussed till now, which of the following data structure will be more ideal for implementing DQ in data structure? What I mean by ideal is the time and space complexity for implementation strategy that you decide should be minimum. The options that we have are circular array, singly linked list, and doubly linked list. It will be interesting to see how many of you guys will get this right. So guys, do leave your answers to this question in comment section below. In a week's time, we'll be announcing the right answer and you all can check it out. On that note, let's dive further and understand the representation of DQ using circular queue. And yes, circular queue is one of the answers for previous questions. We'll understand why it is best in upcoming slides. But please check the complexity analysis of other two strategies to decide your answer for the previous question, as multiple answers can be accurate for that question. Now let's understand what a circular queue is. Well, a circular queue is nothing but the extended notion of linear queue, as it follows the first in first out principle, with the exception that the last position of this particular queue is connected to its first position, making a circular link. This circular link is responsible for naming of this queue as circular queue or ring buffer. Let's understand how a circular queue operates with the help of simulation. This is the illustration of a circular queue having size 5. As the position of rear pointer keeps increasing, a new element will be inserted in this queue until the rear pointer reaches the end of queue. But what if we perform DQ operation now? If we perform the deletion, then the empty space will get created at front of queue. However, this space can further be utilized in this particular type of queue by making circular incrementation of rear pointer or circular link. So, if we increment the rear pointer from its index 5 to index 0, we can utilize empty space by making new insertions. Using this feature of circular queue, we can implement both insertion and deletion at both the ends of queue. Let's understand how we can do that in upcoming slides. The first type of insertion is a pretty ordinary one. In this insertion, we'll increment the position of rear pointer to insert a new element. The arrow shown in blue is rear pointer and the arrow shown in orange is the front pointer. So as you can see, once we increment the rear pointer, new elements get inserted. This is how the insertion using rear node happens. Now, what if we want to perform insertion using front end? In order to perform the insertion using front node, we'll have to make front pointer reach to the end of queue. The only possible way to achieve that is to set front pointer equal to max size minus 1 manually. This command will allow a front pointer to reach the end of queue for performing insertion. And for further insertions, we'll just have to decrement the front pointer location for inserting new elements. This is all about insertion. Now that we have implemented insertion from both ends, let's move on to the deletion operation. Primarily, we'll look into the deletion using front node. In order to delete elements using front node, we'll have to increment the front pointer until it reaches the end of queue. And once it reaches the max size, we'll use circular incrementation to bring the front pointer to the beginning of queue. While performing these incrementation, meanwhile the elements will be removed from the queue. Next up is deletion using rear end. For performing deletion using a rear pointer, we'll have to decrement its location. Once we decrement the rear pointer location, the element will get removed from the queue. Now moving ahead, we'll look into the different operations that can be performed on a double-ended queue. Basically, there are 4 primary operations in the DQ which we have already understood in the representation of DQ using circular queue. These operations are insertion and deletion at the front and insertion and deletion at the rear. Additionally, the circular queue implementation of DQ cost us big of 1, which is the most optimal complexity that we can hope for. Having said that, let's dive into the implementation of these operations using a circular queue. We'll implement the double-ended queue using circular queue. In order to do that, we'll use C programming language and one-dimensional arrays. So without wasting any time further, let's move to the code editor. Now, in order to get started with implementation of DQ, we'll have to create array and pointer variables. So let's do that. Int, we'll name this array as DQ and we'll provide 100 as initial size. Next, we'll create pointers and rear is equal to -1. Now, we'll also define the maximum size for our queue using define call. Size as 5. After done with this initialization process, we'll start working on insertion from front node. We'll declare a function named as void front insert. So let's do that. Void front underscore insert. And inside this function will pass an argument int z to insert an element. Now, while performing insertion, we should always check if the queue is full or not, because if it is full, then the insertion won't be possible. So for that, we'll write condition if front is equal to 0 and rear is equal to size -1 inside and braces or front is equal to rear plus 1 printf DQ is full insertion it's not possible. Okay. Otherwise, if both the front and rear node are pointing to null memory index or -1, we'll manually set our front pointer to index 0 to make the first insertion into the queue. And we will insert the element at new location or index 0 where the front pointer is pointing. So for that, what we'll do is we'll write another condition with else if block. Else if front is equal to -1 and rear is equal to -1, then make front is equal to rear is equal to 0 and dq front is equal to z. Now, if we want to insert the element at the last node of Q, then we need to set front pointer to the max size -1 location. To do that, we'll write this condition, else if front is equal to 0, then front is equal to size -1 and dq front is equal to z. If all these above mentioned conditions fail, then the front pointer is already at the last part of Q and it just need to decrement its location for inserting element in empty spaces as discussed previously. So to do that, we'll write one more condition using else block. So let's do that. Else front is equal to front -1 and dq front is equal to z. Now we have successfully implemented our front insert function. So let's move forward and work on another function that is called as void rear underscore insert, and we'll pass z as an argument to insert an element. Now, as done previously, we will first check if our queue is full or not. So let's do that using if condition. If front is equal to 0 and rear is equal to size -1 inside braces, or front is equal to rear +1, then printf dq is full. Next, if there is no element in an array, we'll manually set the rear pointer to index 0 for new insertion. So for that, we'll write condition else if front is equal to -1 and rear is equal to -1, then set rear is equal to 0 and insert dq rear is equal to z. Otherwise, if rear pointer is already at the end of Q, then we will bring it to the beginning of Q. So for that, we'll write condition else if rear is equal to size minus 1, then bring rear to index 0 and dq rear is equal to z. If all these mentioned conditions fail, then what we'll do is we'll write else condition and we'll simply increment our rear pointer to make an insertion. So for that, what we'll do is we'll create else block and we inside it we will do rear plus plus and we will set dq rear is equal to z. With this, we have successfully implemented void rear insert function. So now let's move into deletion functions. First, we'll create void front dq function, void front underscore dq. And there is no need for any argument for this function. To begin with this function, first we'll have to check if dq is empty because we cannot delete elements if there is no element to delete. So for that we'll write if condition if front is equal to minus 1 and rear is equal to minus 1, then printf there is no element to delete inside this dq. In the next condition, we'll check if there is only one element inside the dq. If there is only one element, then we'll set both front and rear to minus 1 manually. For that, what we'll do is we'll create else if condition. Else if front is equal to rear, then printf we'll add slash n to take this to the next line. The deleted element from the front is modulus d comma dq front. And we will set front is equal to minus 1. Similarly, rear is equal to minus 1. Now, if both these above mentioned conditions fail, then we will delete the element from our front node. The first removal will be in a case when the front pointer is at the end of Q. So for that, we'll write condition else if front is at end of Q, that is size minus 1. Then what we'll do is we will printf slash n the deleted element from the front edge modulus day, comma dq front, comma. And another condition will be when the front pointer is at the beginning section of a queue. For that, we'll write else condition printf /n the deleted element from the front edge modulus d, comma dq front. With this, we have successfully implemented our front DQ function. Now let's move towards next function, that is deletion from the rear end. For that, we'll create new function named void DQ underscore rear. And this function also does not need any argument. So next, what we'll do is we'll create condition to check if the queue is empty or not. So if front is equal to -1 and rear is equal to -1, then printf /n there is no element to delete inside the queue. Now let's move to the next condition. In next condition, we'll write else if front is equal to rear, then printf some statement and set front is equal to -1 along with rear is equal to -1, and that statement will be the deleted element from the DQ using rear node edge modulus d, comma DQ rear. Now, if both these above mentioned conditions fail, then we'll have to delete the element from our rear node. The first removal will be in a case when rear is at the beginning portion of a queue. For that, let's write a condition else if rear is equal to 0, that is at the beginning part of queue, then printf some statement and rear is equal to size -1, that is setting it to the max size of queue, and the statement that we will return is \n the deleted element from the rear node edge modulus d, comma dq rear. In other cases, we'll just have to decrement the size of rear pointer and delete the element. So for that, we'll write else condition printf some statement and set rear is equal to rear minus 1. That is decrementing the size of rear pointer, and the statement that will write is \n, the deleted element from the rear node is modulus d, and comma dq rear. Well, here is one spelling mistake, so let's remove it. Okay, so with this we have successfully implemented our void dq rear function. Now we will implement one more function to display the state of our dq. The name of that function will be void display, and this function also does not need any argument. So we'll begin with implementation of this function. For this, we'll create an iterator element and we'll set it to the front pointer, and we'll printf \n elements inside the double ended queue are next line. We'll enter into while loop to print those elements. I not equal to rear printf modulus d comma dq I, and will increase the value of I by I plus 1 modulus size, and outside this while loop we will printf modulus d dq rear. Okay, with this we have implemented all the required functionalities for our DQ. So let's work on driver method, that is main function, in order to check the output of our program. So let's work on this main function. First, we will insert few elements into our queue. So I will insert first element using front insert. Next, let's insert one more element from front node using function front insert, and this element will be 23. Next, we'll insert elements using rear node underscore insert, and we'll pass 17 now. Next, we'll insert $12, and we'll insert one more element using this rear node only, insert 47. Now we will display the state of our queue after performing all these operations. And next we will dequeue few elements. So for that we'll use front dequeue function, and next we will dequeue from rear node. So dequeue rear And after performing deletion operations, we'll also display the state of our queue. So let's call display once again, and let's add one more command, return 0. Okay, so with this we have successfully implemented our program for DQ implementation. So let's run it and check if it is working fine or not. Okay, so we are getting output here, but our display function is printing output in weird manner. So let's work it out. So all we have to do is we'll have to add space before modulus d here and here as well. So once done with this, let's recompile our code. Okay, so now our output is clear. So let's check if it is perfect or not. So the first insertion that we made was -5. Second was 23 from the front end. So 5 should be getting inserted before 23. So -5 is getting inserted before 23, but as we are inserting it using front pointer, so 23 is remaining at the front now. After these two insertions, we are performing insertions using rear pointer. The first rear insertion was 17, then 12, then 47, and these elements are getting inserted. So let me show you how they are getting inserted in exact same order. So look here. So elements inside the double-ended queue are 23, -5, 17, 12 and 47. That means the insertion is in right order. After that, we deleted the element from front node. So the front node is at 23, so 23 is getting deleted. After that, we deleted the element using rear node. So 47 is getting deleted from the rear node. We are still getting 23 here. That means the DQ function is incomplete, so we'll have to change it. So let's go to the DQ function, and I guess it was from front end. So we'll need to change code for our front DQ. So okay, so in this case we haven't brought our front pointer to index 0, so let's do that here. And once we do this, let's recompile our code again. Okay, so now you can see that the 23 is getting deleted. With this, we have successfully implemented our DQ function. Now let's move back to the PowerPoint and understand few applications of DQ. The first application that we are going to discuss in detail is palindrome checker. You all must have heard about the term palindrome. The palindrome is a specific word or number which reads the same backward as forward. For example, the word radar. It reads the same from both the ends. So using the DQ, we can implement the palindrome checker program with complexity big of 1. The string which you need to check will be inserted into a DQ, and after that it will read from both sides. If the reading is the same, then that string will be considered as palindrome. The next application of DQ is its use in multiprocessor scheduling. But what precisely is multiprocessor scheduling and why do we need it? Well, the system implemented in the old days used single processor scheduling to manage the computing processes. When multiple processes need to be executed by a single core or CPU, then the process takes more time to implement, and thus the system lacks computing power. But the multiprocessor scheduling implemented in modern computers resolves that problem using a double-ended queue. Suppose we have three processors in our system, and each processor has some processes to execute. Each processor maintains a DQ that contains threads that are ready to execute. The processor executes a process, and if a process creates a child process, then that process will be inserted at the front of the DQ or parent process. Suppose the processor P2 has completed the execution of all its threads. Then it steals the thread from the rear end of processor P1 and adds it to the front end of the processor P2. The processor P2 will take the thread from front end. Therefore, the deletion takes from both the ends. This is also known as a-still algorithm in process scheduling.
What is a stack? So, to define stack in a more generalized way, we can consider stack as a linear data structure that follows LIFO order or last in, first out order. Or another way of putting it down is first come, last out order. So, some of the basic operations that can be performed on stack are insertion and deletion, and that can be done only at the end, which is called as the top of the stack. Now, let us understand the basic operations on stack. So, the three fundamental operations that can be applied onto a data structure like stack are push, pop, and peek. So, the push operation involves inserting a new element from the top of the stack. The pop operation involves removing the element from the top of the stack. And finally, the peek operation, which returns the topmost element from the stack without removing the element from the stack. Now we shall go through some generalized examples of stack. So some of the generalized examples of stack are, you can see a stack of books here and a stack of utensils, stack of coins and stack of dollars or bills. Now, let us go through a practical example based on stack in data structures. We shall be using C programming language for this particular example. So you can see that on my screen I have an example for stack data structure. Don't worry about the code. This code will be attached in the description box below and you can always have access to it, and you can run the same code in your personal system so that you have a deeper and better understanding of the program. Now let's quickly run this program. So there you go. You can see the program is getting executed now. So you can see that the program got successfully executed and the elements are being inserted into the stack. Now the elements are A, B, and finally the elements are popped back again, that is B, A, and the last element that is popped away from the stack is A, and you can see that the stack is currently empty, so top is pointing to -1. Now with that, let's get back to the presentation again. Now let us understand some of the applications of stack. So one of the applications of stack is function call or recursion. The recursive function call is also known as the called stack. Whenever a function is called, then the function goes to the top of the stack. Now another important application of stack is expression conversion. There are three types of notations, that is prefix notation, infix notation, and postfix notation. So these particular notations can be taken care by using stacks in real time. Now the next one is checking parentheses. Stack is used to check if the given parentheses are balanced or not. Sometimes if you forget to add a parenthesis, then the compiler will throw an error. So using stack, this can be found if there are balanced parentheses used in your program or not. Balanced parentheses means opening and closing brackets are of the same type. That means if you have two open flower brackets, then you need to have two closed flower brackets. It should not be unequal. It should be completely equal to complete the code segment. Now another application of stack is expression evaluation. Stack can be used to evaluate the expressions. As you can see here, we have an expression that is 6 plus 2 star 3 minus 12 divided by 4. Now this particular expression will be evaluated based on the precedency table. So the stack is used to check the precedence and then the expression gets evaluated into the result, which is 21 right over here. Now another application is the Tower of Hanoi. Tower of Hanoi is a mathematical puzzle which consists of 3 rods and n number of discs of different diameters. All the discs are placed on one rod, one over the other, and in ascending order of size, similarly into a cone-shaped tower. Now we will enter into the next segment where we will discuss about queues. So what exactly is a queue? A queue is a linear data structure that follows the FIFO order, that is the first in, first out, whereas stack followed first in, last out. So this is one of the fundamental difference between stacks and queues. So we'll be discussing those in the next section. For now, let's continue with the operations on queue. The queue is an ordered list in which insertion is done at one end, that is called rear, and deletion is done at another end, which is called front. The operations on queue are enqueue operation that adds a new item to the queue. If the queue is complete, then there is an overflow condition. Dequeue operation is the operation which deletes an item from the queue, and if the queue is empty, then there is an underflow condition thrown as an exception. Now let us understand some of the basic examples of queue. You can consider the patients at hospital registration, and you can also consider an example of customers making use of ATM. Now let us understand the types of queue. So there are basically three types of queues. Those are circular queues, doubly ended queues, and priority queues. Now let us understand the circular queue. In a circular queue, the last element points to the first element to form a circular link. Circular queue is also known as ring buffer. Insertion is done at the rear and deletion is done at the front, as discussed before. Now we will go through the doubly ended queue. In doubly ended queue, both insertion and deletion can be done at both rear and front of the queue. Now the last one, the priority queue. In the priority queue, the nodes have same predefined priority. Insertion can be done as the arrival of the nodes. Node having the least priority will be the first node removed from the queue. Now we will go through a general practical example of queues, and then we will go through the applications of queues. Now on my screen you can see an example for queues. Don't worry about the code. This code will be attached in the description box below, and you can always have access to it and learn executing this on your own system. So without further ado, let's start to execute this code. So you can see that the code got successfully executed and the terminal is asking for us to give an operation. So the first one is to insert an element into the queue. Second one is to delete an element, and the third one is to display the elements in the queue, and the fourth one is to quit. Let's insert. So now let us insert an element into the queue, that is 10. Now let's try to display the elements in the queue. For that I need to select the option number 3, and there you go, the queue has element number 10. Now let's try to delete that element. For that we might have to choose the second option. So you can see that the element got deleted from the queue, and the element deleted from the queue is 10. And you have another choice now. So let's try to quit it now. For that I need to select the option 4, because we have seen how to insert, view, and delete the element. Let's not make further delay, and let's quickly enter into the next part of our session, that is the application of queues. So the first application of queue is breadth first search. Breadth first search, or BFS, traverses a graph in a breadthward direction and uses a queue to remember the next node to start a search. The second application is level order traversal in tree. Level order traversal processes all the nodes of a tree by depth. First the root, then the children of the source. Next one is first come, first serve CPU scheduling. First come, first serve FCFS is an operating system algorithm that works on queued requests and implements them according to their arrival. Now, the Fibonacci heap. Fibonacci heap is a data structure that implements priority queue operations consisting of the collection of heap order trees. Now, our last segment, that is the comparison between stack and queue. So at first, both stack and queue are linear data structures, and stack follows last in, first out, whereas queue follows first in and first out. And when you're considering stack, the insertion takes place at the top and deletion takes place from the top as well. Whereas when it comes to stack, the insertion starts from rear, but deletion or elimination of the element from the queue starts from the front. In stacks, the insert operation is called as push, and deletion process is called as pop. In queues, the insertion is called as enqueue and deletion is called as dequeue. In stacks, we mainly maintain one pointer to access the list, that is called top, which always points to the last element present in the list. In queues, we maintain two different pointers. The first one is the front pointer, which always points to the front element or the first element inserted in the list. And the next one is the rear pointer, which always points to the rear or the last element inserted into the list. Stack is used in solving problems that work on recursion, whereas queue is used in solving problems having sequential processing. So these are the fundamental differences between stacks and queues. What is a tree data structure? So what exactly is a tree data structure? The tree is a non-linear data structure that consists of nodes and is connected by edges. I know it's a little difficult to understand just by the definition, so let me show you the pictorial representation. As you can see, we have the elements, that is 10, 20, 30, 40, 50, 60 and 70, and all these are stored in the tree data structure. They are stored in a non-linear structure. If we had used arrays, it would have been in a linear consecutive way where 10 starts first and 70 ends at the last position. Now, in the next section, we will discuss why we had made to a switch to the tree data structure when we already had a linear data structure, that is array. Now the next topic, that is why we need tree data structure. So there are many reasons why we had switched into tree data structure, and one of the reasons is a linear data structure always stores the elements in a sequential form, that is one after the other. And in operations to be performed in linear data structure, the time complexity increases as the data size increases. You can see here that, as discussed before, the elements are stored in a linear form, that is 10 at the first place and 70 at the last place. Imagine you wanted to access the element 70. Then using the traversal, you had to start from the first position, that is 10, 20, 30, 40, and slowly at the end is 70. So accessing that particular element is really time consuming. We are facing this just for 70 elements. Imagine if we had 700 elements, right? So that is exactly why we had made a switch to tree data structure. And using tree data structure, we have many advantages, as the tree data structure is completely non-linear and it allows easier access and quicker access of the data elements. How is that possible? We will look into it into the next segment, where we will discuss about the traversal of trees. Now, before we understand the traversal of trees, we should understand another important topic, that is the terminologies of tree. So the first one is the node. Node is the entity that contains the keys and pointer to its child nodes. So here you can see that the elements A, B, C, D, E, F and G are the elements. So each and every element, or the blue dot, is called as a node. And the blue dots here are 1, 2, 3, 4, 5, 6 and 7. So we have 7 blue dots. So we have 7 elements here. So you can see the line between each element, right? So this particular line is called edge. Now we'll discuss about the edge in the next part. So the connecting links between any two nodes are called as edges. So we discussed about the nodes, right, where the element is stored. The blue dots are the nodes, and the lines connecting between the elements or nodes is called as the edge. So out of all the nodes, this first node, that is the element A, is called as the root node in a tree data structure. So indirectly, root node is also called as the parent node of all the nodes. Now we will understand what are parent nodes and children nodes. So in a tree data structure, the node, that is the node's predecessor, is called as parent node. So here we have discussed that A, or the root node, is the parent of all nodes. So for A, B and C nodes are children nodes. And for B and C nodes, A happens to be the parent node. Similarly, D and E are the children nodes of B, and F and G are children nodes of C. And the nodes D and E have B as the parent node, and the nodes F and G have C as the parent node. Now followed by that, we will understand the descendant node. So as discussed before, the descendant node is the node that comes after the parent node. Here, the B and C are the descendants of A, and D and E are descendants of B, and similarly F and G are the descendants or children of the node C. So in a tree data structure, the node which does not have any child is called as the leaf node. Now at the end we have D, E, F and G. So these particular nodes do not have any children nodes like B and C. So these particular 4 nodes which do not have any children are called as the leaf nodes. In a tree data structure, the node with at least one child node is called as the internal node. So here the internal nodes are B and C, which have at least one child. In a tree, the total number of children of a node are called as the degree of that node. So in this particular diagram, the degree of a root node is 2 because it has 2 child nodes, and the degree of B is 2 as it has 2 child nodes. Similarly, the degree of C is 2 because it has 2 child nodes. But when it comes to D, E, F and G, the degree is 0 because they do not have any child nodes. In a tree data structure, the root node is said to be at level 0 and the children of the root node are said to be at level 1 and the children nodes of the level 1 are at level 2. So to understand this, let's go through the diagram. As you can see, this particular root node is called as level 0 and followed by that we have the children nodes of A, that is B and C, and that level is called as level 1. And followed by that we have level 2, and if this tree goes forward, the levels also increase accordingly. Now in a tree data structure, the total number of edges from a leaf node to the particular node is the longest path, and this particular path is called as the height of that node. Now here we have our general tree data structure, and here you can see the height of node A is 2. And the height of node B and C together is at 1. And the height of the last leaf nodes happens to be 0. Next, in the tree data structure, the total number of edges from the root node to a particular node is called as the depth of that node. Now in this particular tree data structure, the depth of the root node is 0. And the depth of B and C together is 1 because the number of edges connecting to the node A from B is just 1, and similarly the number of edges connecting the node C from A is just 1. So the depth of both B and C is 1. Now if we consider the last leaf nodes, then the depth is 2 because if you see, G is connected to A using 2 different edges. Similarly, F is connected to A using 2 different edges, and E and D also have 2 nodes to connect to A. So the depth is 2. Now in the next segment, we will understand the tree node. So the tree data structure has data part and references to its left and right child node in the tree data structure. So here you can see this is the node, and the node has 3 segments, that is data element and the references to its left child and the references to its right child. Now there are 4 different types of trees. The first one is the binary tree, followed by that we have the binary search tree, then we have AVL tree, and finally we have the B tree. Let us discuss each one of them. The first one is the binary tree. A binary tree is a tree data structure in which each parent node at most has 2 children. So in this particular tree, we'll have at most 2 children. That means it might have 1 or more than 1, but not more than 2 children per node. Moving ahead, we have the binary search tree. So a binary search tree or a BST is a tree data structure in which each node has a maximum of 2 children. All nodes of the left subtree are less than the right node. All nodes on the right subtree are more than the root node. So here you can see the image or the GIF which represents the image of a binary search tree. So here all the nodes of the left subtree are less than the root node and all the nodes of the right subtree are more than the root node. The next type of the tree is the AVL tree. The AVL tree got its name after inventory Georgi, Adelson, Welsky and Landis. AVL tree is the self-balancing tree in which each node maintains a balance factor whose value is either 1, 0 or -1. Balance factor is equals to height of the left subtree minus height of the right subtree or height of the right subtree minus height of the left subtree. So in this particular image, you can identify it is an AVL tree. And now the last type of tree, that is the B tree. B tree is a special kind of self-balancing search tree in which each node can contain more than one key and can have more than two children. B tree is also known as the height-balanced M-way tree. Now in this particular GIF, we can see how a B tree looks like. Now followed by this, we will discuss the tree traversal. So traversing a tree helps to visit required node in the tree to perform specific operations. Tree traversal can be performed in three different ways. The first one is the pre-order traversal, where we visit the node and visit all the nodes from the left side, then visit all the nodes from the right side. So this particular GIF is an example for pre-order traversal, where we visit all the left side nodes first, then we visit the right side nodes. Now we will move ahead into the next type of traversal. That is the in-order traversal. First, we visit all the nodes from the left side, then we visit the root node, and then we visit all the nodes from the right side. So this particular GIF will be an example for the in-order traversal, where we visit all the left side nodes, then we visit the root node, and followed by that we will visit the right side nodes. And the last type of traversal is the post-order traversal, where we visit all the nodes from the left side first, then we visit all the nodes from the right side, and finally visit the root node. So this particular image on the right side is an example for post-order traversal. Now before we get into learning the applications of trees, we will try to execute one example based on the post-order, pre-order, and in-order traversals in tree data structure. So you can see that we have an example on my screen right now. So here we have the node structure, then we have the in-order traversal function, followed by that we have the pre-order traversal function, and finally we have the post-order traversal function. Now let's quickly run this program and see the output, and don't worry about the code. This particular code document will be attached in the description box below and you can have access to it. Now we have the run option over here and the program got successfully executed. You can ignore this warning, and here we have the in-order traversal of the tree in the first output. Then we have the pre-order traversal of the tree, and finally we have the post-order traversal of the tree. Now let's discuss the last part, where we will learn the application of trees. So the application of trees are as follows. Binary search trees are used to quickly check whether an element is present in the set or not. Then we have the most popular database usage of B tree, which is a variant of tree data structure. Then we have the modified version of trees called as tries, which is used in the router to store routing information. And finally, the compiler uses a syntax tree to validate the syntax of every program you write. What is tree traversal in data structure? Tree traversal is a process of visiting each and every node in a tree data structure. So right here on my screen, we have a tree with different nodes, that is A, B, C, D, and E. So here we will be visiting all the nodes one after the other using the tree traversal methods. Now that we have a brief understanding of what exactly is a tree traversal process, let's get into the next topic of our discussion for today, that is the data structure used for tree traversal. In a tree data structure, there are primarily two data structures utilized for tree traversal. The first one is the stack data structure and the second one is the queue data structure. A stack is a linear data structure that operates on the last in, first out, LIFO principle. There is only one pointer in the stack, that is the top pointer, which points to the stack's topmost element. Only the top of the stack is used for insertion and deletion. Now the next one is the queue. A queue, unlike stacks, is open on both the ends. The one end is always open and used only for input, and the other is only used for deletion or elimination. The principle followed in queue is first in, first out, or FIFO approach. Followed by that, we will look into the different types of tree traversals in data structure. Tree traversal can be done in the following ways. The first one is breadth first search and the second one is the depth first search. First, let us have a look at the breadth first search algorithm or breadth first search traversal. We follow level order traversal in breadth first search. Breadth first search traverses nodes by level instead of subtrees. First, we visit the root node. Followed by the root node, we visit the left subtree of the tree. Then, followed by the left subtree, we finish the right subtree of the entire tree. After that, we go until the leaf nodes of the entire tree is found. The second one is the depth first search. In depth first search, we traverse tree data structure in three ways, that is pre-order traversal, in-order traversal and post-order traversal. Let us take a look at how these traversals are carried out. First, let us discuss the pre-order traversal. We traverse the root node first in the pre-order traversal. Then we traverse through the left subtree and finally we traverse through the right subtree. Then there is in-order traversal. In-order traversal involves traversing of the left subtree first, followed by that we enter the root node, then we visit the right subtree. Lastly, we have the post-order traversal. So post-order traversal involves traversing of left subtree first, then the right subtree, and finally we visit the root node. Now next, we will have a look at some of the important applications of tree traversal in data structure. So we use tree traversal in data structures to build a prefix expression or Polish notation from expression trees. Then utilize the pre-order traversal and then traverse the expression tree in a pre-orderly manner. A binary tree's postfix representation or reverse Polish notation can be generated using post-order traversal. Because it returns values from the underlying set in order, according to the comparator setting up the binary search tree, in-order traversal is often employed on binary search trees. A complete binary tree can be deleted or released when deleting or freezing nodes and values in the post-order traversal. Now, next we will see an example based on tree traversal in data structures. So on my screen we have an example for tree traversal in data structure. To begin, we have included the enum or user specified data type traversal. It mostly used to give integral constant names which make a programmer easier to comprehend and maintain. We defined three variables in the enum data type, that is pre-order, in-order and post-order traversal. We can define the type that can take one of the two values by using the typedef and enum keywords. We have a traversal data type with trav variable and a node data type with node variable. Then we define the node using the data structure type as struct node. We declare one variable x and two nodes as a left and a right nodes respectively in this node section. We then attempted to create node using the create node function, passing the root node as an argument. In this code, we use a malloc function to create a node, assign data to x and null to both the right and left nodes before returning to the root node. If node t is not equal to null, we simply return it. Otherwise, we will use the released tree function to release the left and right nodes. And if neither is a root node, then we will use the free function to release the node t, which will behave as the root node. Then we define the display tree function, which takes the trav variable and the root node as parameters. There is a condition in this function, that is, if the root node is not null, we will return the root node. Then, using the switch case scenario, we attempted to traverse the tree using all three types of traversals. We utilize a trav variable in the switch function, so if any of the in-order, pre-order or post-order variables match the trav variable, the traversal will be executed. Then, we created a tree using the create tree function, which takes a data variable as input. In the create tree function, we used a malloc function to create the root node, and we first assigned null to the left and right nodes, as well as the data to the variable x before returning to the root node. We first traversed the root node, then the left subtree and finally the right subtree in the pre-order traversal case. In order traversal case, we first traverse the left subtree, then the root node, and finally the right subtree. And in the post-order traversal case, we traverse the left subtree, then the right subtree, and finally traverse through the root node. And finally, we exit the display tree function and moved on to the main function. We assign the values 5 as the root node, then 10, 20, and 30 as the left nodes, and similarly 15, 25, and 35 as the right nodes, and then we call the 3 tree traversals, that is pre-order, in-order, and post-order, to traverse the tree. And finally, we release the root node. Now, let us try to execute this program and see the output. So there you go. The program got successfully executed, and you can see that the output has been displayed on my screen. So the pre-order traversal is 5, 10, 20, 25, 15, 30, and 35. Followed by the pre-order traversal, we have the in-order traversal, that is 20, 10, 25, 5, 30, 15, and 35. And finally, we have the post-order traversal, that is 20, 25, 10, 30, 35, 15, and 5. And with that, let me give you a simple question. So what is the pre-order and post-order traversal of this binary search tree? So the elements are 1, 2, 3, 4, 5, 6, and 7. You need to find out the pre-order and post-order traversal of this binary tree, and you can let us know the answer in the comment sections below. What exactly is a binary tree? So it is a tree data structure in which each node can have at most 2 child nodes. These nodes are referred to as left child node and right child node. Next, let's discuss about some terms related to binary tree. First up, a node. A node consists of data and linked to its both child nodes. Next, the root node. Root node is the first node of the tree. Next, leaf nodes. These are the nodes which has no child. Next, parent node. Apart from the root node, any node which has at least one child is called as parent to that child node. Next up, a child node. Any node with a parent is called as a child node. Next up is the internal node. Any node with a child and a parent is called as an internal node. Next up is the height of the binary tree. The longest path from the root to any leaf node is called as the height of the binary tree. Next up is the depth of the binary tree. The depth of the node is the total number of edges from the root node to the target node or the last child node. Now let's try to implement the binary tree in the code editor. As you can see, now we are on the code editor, and the code on my screen is an example for binary tree. Now here you can see that we have created a structure for node, followed by that we have a function where we will print the tree, and this is our main function. Now don't worry about the code. This particular code segment will be available in our description box below, and you can always have access to it and try to edit and run this code on your own local system to have a better learning experience. Now without further ado, let's try to run this program quickly and see the output. So there you go, the code got successfully executed, and here you can see the output of this particular binary tree. Now let's get back to the theory part. So as discussed before, followed by the implementation part, we will learn about the properties of a binary tree. Now let's discuss the properties of the binary trees. First up, maximum number of nodes at a level L is 2 to the power L. Next up, maximum number of nodes in a binary tree of height h is equals to 2 to the power of h minus 1. Next up, minimum possible height in a binary tree with 2 nodes is equals to log of L plus 1 base 2. Next up, the minimum possible level in a binary tree with n nodes is equals to log of L plus 1 base 2. Finally, a binary tree with L leaves has at least log L base 2 plus 1 levels. Now, let's discuss about the different types of binary trees. First up, we have the full binary tree. Followed by that, we have the complete binary tree. Then we have the perfect binary tree. Followed by that, we have the balanced binary tree. And lastly, the degenerate binary tree. Let's discuss about these in detail. First up, full binary tree. A full binary tree is a unique tree data structure in which a node can have either two children or no child. Next, a complete binary tree. So a complete binary tree is another specific binary tree where each node on all levels except the last level must have two children, and at the lowest level, all leaves should reside possibly on the left side. The next one is the perfect binary tree. A binary tree is perfect if every node must have two children and every leaf is on the same level. The next one is called as the balanced binary tree. A binary tree is balanced if for each node the height of the left subtree and the height of the right subtree varies at most by just 1. At last we have the degenerate binary tree. A binary tree is said to be degenerate if every internal node has only one child. We have now discussed the binary tree, some terms and properties related to binary trees, and types of binary trees. Now we will look into the operations that needs to be performed on the binary tree. So there are basically three types of operations that can be performed on binary tree, which are traversal, insertion, and deletion. So first we'll look into the traversal operations. There are three different types of traversal operations possible on binary tree, which are pre-order traversal, in-order traversal, and finally the post-order traversal. Now let's get back into the text editor mode and try to execute our example. So right now we are on the text editor, and this particular code is for the traversal operations on our binary tree. And here you can see we have the structure for node, and we have also the in-order function, pre-order function, and post-order function. And don't worry about the code. This particular code will be available in the description box below. And after you have written the code, we have some standard input over here. You can see that we are giving the number of edges as 4, and the left subtree elements are 2 and 1, and the right subtree elements are 2 and 3, and another left subtree elements are 3 and 5, and lastly we have 5 and 6 for another left subtree. Now let's try to execute this code. Now we have already executed the code, and we also have the output over here, and here you can see we have entered the number of edges as 4, and the traversal is in-order traversal, which is 1, 2, 6, 5 and 3, and the pre-order traversal output is 2, 1, 3, 5, 6, and the post-order traversal is 1, 6, 5, 3 and 2. Now let's get back to the PPT. Now we have the insertion operation. And now let's get back to our text editor and try to see an example for insertion operation as well. So on my screen you can see an example for insertion operation. So here we have the insert function. As I said, this particular code will be available in the description box below. Now let's provide the standard input. So the standard input will be 4 edges, and we have 2 and 1 as the left subtree, and 2 and 3 as right subtree, 3 and 5 as left subtree again, and 5 and 6 as the left subtree. Now let's quickly run this code, and there you go, the program got successfully executed, and here we have the output. The nodes got inserted, and it has provided an in-order traversal, that is 1, 2, 6, 5 and 3. Now let's get back to the presentation, and the last type of operation is the deletion operation. Let's quickly execute an example based on deletion operation as well. Now as you can see, we are on the text editor again. Now here the example is for deletion operation. We have the delete function over here. Now for this particular program we don't need any standard inputs, so just let's run the program. So there you go, the program got successfully executed, and we have the output over here. And in order traversal before deletion, and in order traversal after the deletion of an element. So the deleted element is element 11. Now with that, let's get back to the presentation mode again. So that's how the element got deleted. Now we have reached to the last part of this session, that happens to be the final key takeaways. So What are the final takeaways? So binary tree is faster at search operations than other type of tree, and it is easier to find maximum and minimum elements in the binary tree. Binary tree does not allow duplicate values, and graph traversal is done using binary tree. It is used to convert the postfix expressions into the prefix expressions.
Let's get started with introduction to binary search tree. Binary search tree is a set of nodes organized in such a manner that they all have the same binary search tree characteristics. A key and a value is assigned to each node. The requested key is compared to the keys in binary search tree. So during search, if the key is found, then the corresponding value will be retrieved. Next up, properties of binary search tree. First up, the left subtree of a node contains only nodes with keys lesser than the parent node. Next up, the right subtree of a node contains only nodes that are greater than the parent node. The left and the right subtree each must also be a binary search tree. Next, let's discuss what are the operations we can perform on a binary search tree. First up, insertion. Last, deletion. Let's discuss them in detail. First up, insertion. We can insert a node in such a way so that we obey binary search tree rules. That is, the new node should be either less than the parent node if it's on the left subtree, or if it's on the right subtree, it should be greater than the parent node. Let's execute this in the code editor. We will start by creating a class for the binary search tree. So class bst int data and bst pointers left, comma, right. Next, we will define some functions publicly. Public first default constructor, and a parameterized constructor. A function to insert the value. And a function to traverse the node. Now let's write default constructors definition. So bst Now let's write the parameterized constructors definition. bst int value data is equals to value and left is equals to null and right equals to null. Now let's write the definition for the insert function. So bst insert bst star root comma int value. Now we will check if the tree is empty or not. So if root, then we will insert the first node. So we will return new bst value. Otherwise we will insert the data. So if the value is greater than root data, then we have to insert it in the right subtree. So root right is equals to insert root right comma value. Else the value should be inserted in the left side. So root left is equals to insert root left comma value. And then we will return root. Now let's write the traverse function. So void bst traverse bst star root if root then we will return otherwise we will first traverse left side then we will print the root data. And then we will traverse the right side root right Now let's write the main block. So we will start with an empty tree. So bst b comma star root is equals to null. The root is equals to b dot insert root comma 50. B dot insert equals to root comma 10. B dot insert gonna be root comma 30. B dot insert gonna be root comma 50. Sorry, we already used 50, so we will use 60. B dot insert root comma, let's use 20. Let's try to traverse this. So B dot traverse root. Let's execute this. As you can see, we have successfully created and traversed our first binary search tree. Let's get back to slides. At last, deletion. We will delete a node following the binary search tree rules. That is, the value of the left subtree should be less than the parent node, and the value of the right subtree should be greater than the parent node. Let's try these in the code editor. Let's start by creating a node. This time we will use structure. So struct node int key struct node star left comma star right. Now we will create a utility function to create a new binary search tree node. So struct node star new node int item. Struct node star temp equals to struct node star malloc size of struct node. Next, temp will be assigned the key is equals to item. Temp left equals to null and temp right is equals to null. Now let's write a function to traverse the tree, traverse, struct, node, star, root. So if root is equals to null, so traverse root left, cout root e, traverse root right. Now let's write a utility function to insert the new node with the given key in the binary search tree. So struct node star insert struct node star node comma int key. So if node is equals to null, then we will return new node key. Otherwise, we will recur down the tree. So if key is less than the node key, then we will insert in the left subtree. So node left is equals to insert node left comma key. Else node right should be inserting key. Now let's return the node. Now we have given a non-empty binary search tree, so we have to return the node with the minimum key value found in that tree. So we will start struct node star min value node struct node star node struct node star current is equals to node. So we will loop down to find the leftmost leaf. So while current and parents left is not equals to null. So current should be equals to current to return current. Struct node star delete node struct node star root comma int key if root equals to null, return root. Now, if the key to be deleted is smaller than the root's key, then it lies in the left subtree. So we will check if key less than root key, then root left will be equals to delete node root left key. Comma key. Now, if the key is deleted is greater than the root's key, then it lies in the right subtree. So else, if key is greater than root, root right is equals to delete node root right comma key. Else, if roots dot left equals to null and root dot right is equals to null, then return null. else if root left equals to null, then struct node star temp is equals to root right and free root return temp. Else if roots right is equals to null, then struct node star temp is equals to root free root return temp. Now node with the two children get the in-order successor smallest in the right subtree. So struct node star temp is equals to min value node root right. Now we will copy the in-order successors content to this node. So root is equals to temp. Now we will delete the in-order successor. So root right equals to delete node root right comma temp e. Now we will return root. Now let's write the main block. We will start with an empty tree. Struct node star root is equals to null. Now root is equals to insert root comma 2 root is equals to insert root comma 5 root is equals to insert root, comma 3. Root is equals to insert root, comma 4. Root is equals to insert root, comma 7, and root equals to insert root, comma 6. Let's try to traverse this. So C out traversal of the given tree. Traverse root. Now first we will delete a value. So C out delete 2. Now root is equals to delete node root, comma 2. Now C out traversal after deleting traverse root. Let's execute this. As you can see, we have successfully deleted 2 and traversed the tree again. Let's get back to our slides. At last, let's sum up what we have learned from this session. First up, left side nodes are always lesser than the parent's node, and the right side node are always more than the parent node. Next, it is easier to search and sort elements in a binary search tree. Finally, a binary search tree offers faster insertion and deletion operations. What is a B plus tree? A B plus tree is a special m-way tree data structure. A B plus tree of order m can have at most m minus 1 keys and m children. A B plus tree can be used as B tree with only keys to each node and with linked leaves to which an additional level is added at the bottom. Now, let's discuss some properties of B plus trees. First up, every node in B plus tree can have at most m elements. Next, every node except the root and the leaf node must have m by 2 children. Next, maximum keys for any node is m minus 1. And at the last, minimum keys for any node is ceiling of m by 2 minus 1. Now, let's discuss what are the various operations we can perform on B plus tree. We can perform two operations on a B plus tree. First up, insertion. Second, deletion. Now let's discuss these in detail. First up, insertion. We have to insert an element in such a way so that We won't disobey any properties of B plus trees. Now let's try this operation in a code editor. We will start by creating a node. To create a node, we need a struct B plus tree node int start data B plus tree node space star child ptr boolean leaf and int n. For the object star root will be equals to null star np pointer will be equals to null comma star x will be equals to null. Now we will write a constructor for it. So b tree node star init int I and p equals to new b plus tree node and p arrow data is equals to new space int bracket 5 and np child ptr is equals to new b plus tree node star bracket 6 np leaf is equals to true and np at the n is equals to 0. Now we will write a for loop I is equals to 0, I less than 6, I plus plus np child is equals to return traverse b plus tree node star p out and I again a for loop from I equals to 0 to I less than p at n I plus plus If P doesn't have leaf, then we will traverse that child. Traverse P child ptr bracket I. See out. P data at I. Now we will check these conditions again for I at P at N. We will traverse it again from P child at I. See out and L. Now next function will be used to sort this. So void sort int star P comma int N. Int I comma j comma temp for loop j equals to I, j less than equals to n, j plus plus. If P bracket I greater than P bracket j, then we will swap these two. So temp will store P at I and then P will replace its value with P at j. Now we will store the temp value in the P of j. Now let's write a function to split these child. Int split child b plus tree node star x comma int I int j mid b plus tree node star np1 comma star np3 comma star y np3 is equals to init np3 equals to true if I is equals to -1 mid is equals to x data bracket 2 x data bracket 2 will be equals to 0. Then x will store n minus minus p1 is equals to init now when p1 leave will be equals to false and x leave is equals to true. So for loop j is equals to 3, j less than 5, j plus plus. J minus 3 will be equals to x data at j. np3 child ptr at j minus 3 is equals to x at child ptr bracket j np3 n plus plus x data bracket j is equals to 0. Now x greater than n minus minus. Another for loop from j is equals to 0 to j less than 6 at j plus plus rate. X child ptr at j will be stored at null Now np1 data at 0 position will be equals to mid np1 child ptr at np1 on n will be equals to x np1 child at np1 on n plus 1 will be equals to np3. np1 call n plus plus root is equals to np1 now else y is equals to x child ptr at I and mid is equals to y at data at 2 and y on data at 2 is equals to 0. Y will store n minus minus. Now for loop j is equals to 3, j less than 5, j plus plus, np3 data j minus 3 is equals to y data j np3 n plus plus y data bracket j is equals to 0, y n minus minus x child ptr at I plus 1 is equals to y x at child ptr I plus 1 is equals to np3 return now we will write a function to insert into the tree void insert argument as int a so int I, comma, temp x is equals to root. If x equals to null, then root is equals to init and x will be equals to root. Otherwise, if x is leaf, and x at 9 repeat and x at n is equals to 5, then temp is equals to split child x comma -1 x is equals to root. If a is greater than x at data at I, and a is less than x at data I plus 1, I plus plus, and break. Else, if a is less than x at data 0, then break. Else, continue. X is equals to x at child at I. Else, while x leaf is false, for loop I is equals to 0 when I is less than x at n. I plus plus, If A is greater than X at data I and A is less than X on data I plus 1, I plus plus, break. Else, if A is less than X data break. Else, continue. If X child at n is equals to 5, then temp is equals to split child at x comma I x data at xn on n is equals to temp x at n plus plus, continue. Else x is equals to x child ptr I x on data at x at n is equals to a sort x at data x at n x at n plus plus. Now let's write the code for the main block. First we will declare some variables as int I, n and t. Now we will request enter number of element to be inserted. in at n. Now C out. Now we will enter the element. So enter the element now we will write a for loop. So I is equals to 0 to I less than n at I plus plus. So Cn t and insert t. Now we will traverse this tree. So C out traversal of b plus tree. Traverse root. Let's execute this. We will enter 5 elements 2, 3, 5, 7, 9. As you can see, we have successfully traversed our first B plus tree. Let's get back to our slides.
Next, deletion. While deleting any element from B plus tree, we have to be careful not to break any properties of B plus tree. Like, all the leaves must be present at the same level or elements must be in ascending order. Now let's try these operations in a code editor.
Start by creating a B plus tree. First, we will declare a global variable int max equals to 3. Then we will create a class pptree and a class node boolean is leaf int star key comma size node star ptr and a friend class pptree. Now public node variable. Now we will write class pptree so node star root void insert kernel int node star comma node star. void remove internal int comma node star comma node star and a node function find parent node node star. Now public pp tree, the constructor, a search function, a insert function, void remove void display star get root is equals to new int bracket max yeah is equals to new node star bracket max plus 1. BP tree equals to null. Now void B, BP tree insert int x if root is equals to null then root is equals to new node root calls key at 0 stores at xx. The root checks its leaf size is equals to 1. Else node cursor is equals to root node star parent while cursor is leaf is equals to false. Parent equals to cursor now for loop int I is equals to 0 to I less than cursor size I plus plus. If x is less than cursor key at I cursor is equals to cursor at ptr at I. If I is equals to cursor size minus 1 cursor at ptr I plus 1 break. Now if cursor size is less than max, then int I is equals to 0 while x is greater than cursor p at I and then I is less than cursor size. I plus plus. For loop int is equals to cursor at size and j is greater than I, j minus minus. So cursor calls key at j is equals to cursor calls key at j minus 1. Cursor calls key at I is equals to x. Cursor calls size plus plus. Cursor calls ptr at cursor size is equals to cursor ptr at cursor size minus 1. Now cursor at ptr cursor size minus 1. Cursor ptr equals to null. Else node equals to new int virtual node max plus 1. For int I is equals to 0 to I less than max at the rate I plus plus. So virtual node at I is equals to cursor e at I int I is equals to 0, comma j, while x is greater than virtual node bracket I is less than max I plus plus for int j is equals to max plus 1, comma j is greater than I j minus minus virtual node at j is equals to virtual node at j minus 1. So virtual node at I is equals to x. So new leaf is leaf is equals to true. Cursor size is equals to max plus 1 by 2 new leaf size is equals to max plus 1 minus max plus 1 divided by 2 cursor bracket cursor size is equals to new leaf. New leaf at new leaf size is equals to cursor ptr max. Now void BP tree insert internal int x comma node star cursor comma node star child. If cursor size is less than max, then int is equals to 0 while x is greater than cursor at key at I and I is less than cursor of size I plus plus. For loop int j is equals to cursor size j is greater than I j minus minus cursor at key at j is equals to cursor j minus 1 cursor key bracket I is equals to x cursor size plus plus cursor at ptr bracket I plus 1 is equals to child else node star new internal is equals to new node int virtual key is max plus 1 node star virtual key at max plus 1 are virtual PTR at or int I is equal to 0, I less than max, I plus plus, virtual key I is equals to cursor key for int I is equals to 0, I less than max, plus 1, I plus plus, virtual PTR I equals to cursor PTR at I. Node star pp tree find parent node star cursor comma node star child node star parent if cursor is leaf or cursor at ptr 0 is leaf. Then return null. For loop int I is equals to 0, I less than cursor size plus 1 I plus plus f cursor ptr equals to child parent is equals to cursor return parent else parent is equals to find parent cursor ptr child if parent not equals to null return return parent. Now void repeat tray remove int x if root equals to null then cout empty else node star cursor equals to root node star parent int left sibling comma right sibling so while cursor is leaf equals to false so for int I is equals to 0 I less than cursor size and I plus plus parent is equals to cursor left sibling is equals to I minus 1, right sibling is equals to I plus 1. If x is less than cursor is at I, then cursor will be equals to cursor ptr. Now if I is equals to cursor size minus 1, equals to I, right sibling equals to I plus 2, cursor is equals to cursor ptr bracket I plus 1, break bool found is equals to false, suppose for pose equals to 0, pose is less than cursor size pose plus plus. If cursor key at pose is equals to x, then found equals to true, and then break. Now if not found, then out not return. Now if cursor size equals to 0, then cout write, delete, cursor, delete, cursor, PDF, delete, cursor, root is equals to null, return, for loop, int I is equals to cursor size equals to 0, j less than, right node size I plus plus, comma j plus plus, cursor key at I is equals to right node cursor here add cursor size equals to null. Now see out, merging 2 remove internal at right sibling -1 comma parent comma right node delete right node key right node right node. Now void tree display. Cursor if cursor is not equals to null, or I equals to 1, I less than cursor size I plus plus. See out. Cursor see out cursor key at I see out handle if cursor is leave not equals to true, and for int I equals to 0, I less than cursor size plus 1 I plus plus. Okay. Cursor ptr now node star bp tree get root. Return root. Now we will write the main block. We will start with an empty tree, bp tree, node. Now node dot insert 5, node dot insert 15, node dot insert 25, node dot insert 35, node dot insert node dot display node dot get root node dot remove fifteen node dot display node dot get root. Let's execute this. As you can see, this program is working flawlessly. We have successfully deleted the key 15. Let's get back to our slides.
At last, let's sum up what we have learned in this session. First up, B plus trees are fast at performing all its operations. Next, all the leaves must be present on the same level and data is only stored in the leaf node. Next, elements of the B plus tree are sorted in ascending order from the left to the right. Finally, every node contains one more pointer than the number of elements of the node.
A brief introduction to graphs. So what exactly is a graph? So a graph is a data structure like any other data structure, example linked list, arrays, etc. So graph is a little different from the other types of data structures such as linked list and arrays. They are linear data structures, whereas graph is a non-linear data structure that consists of finite sets of vertices and a bunch of edges connecting with them. So what are these vertices and edges? So let us understand that a graph is usually represented by a set of vertices and edges. So a vertex is the node present in a graph. Imagine that you are a group of 5 friends. So each one of you is considered as a vertex and the network connecting you guys is known as an edge. So the overall graph of you people can be considered as G and it is represented by vertices and edges set, where vertices is you and the network connecting you guys is called as an edge. So here you can see it clearly. Each one of the friend is called as a vertex and the network connecting them is called as an edge. And the entire graph is represented using a set of vertices and edges. Now moving ahead, we will understand the graph terminologies. Now at first we have the adjacency vertices and adjacency edges. So what are adjacent vertices? If there is an edge between two vertices, that is one vertex or one node is connected to another node directly using just one single edge, then those vertices are called as adjacent vertices. Now what are adjacent edges? If there is one common vertex between two edges, then those two edges are called as adjacent edges. Let's imagine this way. Let us imagine that we have 3 vertices and these 3 vertices are connected using 2 edges. So here we have one vertex which is common between these 2 edges. So such type of edges are called as adjacent edges. Next we have the degree. In an undirected graph, number of vertices adjacent to the vertex is called as a degree. Next is the path. The path is considered as a sequence of distinct vertices such that two consecutive vertices are adjacent to each other. Up next, we have the cycle. A path that has only one repeated vertices are called as first and last vertices. Followed by that, we have the walk. The term walk is self-explanatory. A walk is the sequence of vertices and edges in the graph, which is used to traverse through one vertex to another vertex. Now we have entered the next segment of this particular tutorial, where we will be discussing the different types of graphs available. So at first, we have the finite graph. So what exactly is a finite graph? A graph is said to be finite when the number of vertices and the number of edges are in a finite number or in a countable number. Now the next type of graph is the infinite graph. So what exactly is the infinite graph? So the infinite graph is a typical opposite of the finite graph. So this particular graph will not have countable number of edges and countable number of vertices. The image here is an example for a typical infinite graph. Now followed by the infinite graph, we have the trivial graph. So what is a trivial graph? A graph is said to be trivial if there is only one single vertex without any edges. So this particular type of graph will only have vertex, that is only one single vertex, not more than one, and there will be no edge. If you have just one vertex, then there is no possibility of having an edge, unless if you have one single loop type of edge, which is connecting to itself. But in a trivial graph, we don't even have that. We just have one single vertex. So followed by trivial graph, we have a simple graph. So what exactly is a simple graph? A graph is said to be simple if there is only one and one edge between each vertex. So this particular example can be considered as a simple graph. So here, each and every set of vertices have one single edge between them. Now followed by the simple graph, we have the multigraph. So if there are multiple edges between the pair of vertices, then this particular type of graph is known as a multigraph. So here you can see that we have two vertices, A and B, and we have two edges connecting them. Not one, but two. But in a simple graph, we were supposed to have just one edge connecting the vertices. So this is the difference between simple graph and a multigraph. So followed by multigraph, we have a null graph. So what is a null graph? A graph is said to be null if there are only vertices and no edges between them. So remember the trivial graph, right? We just had one single vertex but no edges. But here we do have multiple vertices but no edges connecting them. So this type of a graph is considered as null graph. So followed by null graph, we have the complete graph. So what is a complete graph? A graph is called as a complete graph where each vertex must be connected with the other vertices using the edges. So the meaning of this particular type of graph is all the edges are connected to all the other edges using at least one single edge. So here you can see A is connected to B, D and C all together with at least one edge, and similarly all other vertices are connected to each other with at least one single edge. Now followed by the complete graph, we have the pseudo graph. So what is a pseudo graph? A pseudo graph is a graph where at least one vertex will have self-looping type of edge. So remember the self-loop or self-edge we have discussed in the trivial graph type. So this particular type of an edge where it connects to itself is called as a loop or kind of self-connecting edge. So any graph that has this kind of a edge is called as a pseudograph. So followed by the pseudograph, we have the directed graph. So what is a directed graph? Any graph is called as a directed graph where each edge has a direction associated with it. So far we have just discussed the edges which are connecting to one or the other vertex, but there was no direction. But here you can see that this particular edge has a direction, that is from B to A, not from A to B, it is from B to A. This type of edges which are directing the traversal of the graph are known as the directed graphs. Now followed by the directed graphs, we have the regular graph. So a graph is a regular graph where each vertex of the graph has the same degree. Now here you can see all the vertices have the same amount of degree, that is the connection between all the other vertices. So the degree of A is 3, so the degree of B is also 3, and the degree of D is C, and similarly the degree of C is also 3. So what I mean to say is all of these vertices have the same degree, that is 3. Now we have the weighted graph. So what is a weighted graph? A weighted graph is where each edge holds some weight that denotes the traversal cost through those edges. Now here you can see that all the edges have a different weight. The edge from A to B has the weight 5, and the edge from A to C has the weight 9, and the edge from C to B has 2, and the edge A to D has 8, and finally C to D as 7. So all these values are the weight or the cost to traverse from A to another vertex. So from A to B we have the cost 5, and A to C we have the cost 9, and similarly C to D we have 7, and so on. Now followed by the weighted graph, we have the connected graph. So what exactly is a connected graph? A graph is said to be connected where each pair in the graph is connected. Followed by a connected graph, we have the disconnected graph. So it is a typical opposite of the connected graph. A graph is said to be disconnected where each pair in the graph is not connected to each other. Now next we have the cyclic graph. So a graph is said to be cyclic if it contains at least one cycle in a graph, that is one complete traversal connection. So A can be traversed again from traveling A to C, C to D, D to B, and B to A again. So this type of a graph is called as a cyclic graph. Now next we have the acyclic graph. So it is the typical opposite of the cyclic graph. So here you cannot traverse to A again by traversing from A to C, C to D, and there is no connection between D to B. So the complete cycle is not available here. This type of graphs are called as acyclic graphs. So moving ahead, we have the graph representation. So generally, there are two different ways to represent the graph data structure. They are using adjacency matrix and adjacency list. So what is adjacency matrix? So adjacency matrix is a sequential representation. Adjacency matrix is used to represent which nodes are connected to which node. If there is an edge between two vertices, then the value of the corresponding element of the graph is 1, otherwise 0. If there is any weighted graph besides, then zeros and ones, we can store the weight of the edge as that particular number. Suppose that there is a connection between A and B, and it is represented as a weight of 5. Then there is a connection, so we will use the connection as true, but we will not represent it as 1. Instead, we will use the weight, that is 5, to represent it as 5, not as 1. If there is no weight, then we will represent it as 1, and if there is no connection, then we will represent it as 0. Now, undirected graph representation. So here you can see how we have represented a graph. So there is no connection between A to A, that is there is no loop, so the value will be 0. If there was a loop and if it was represented with a weight, then we could have written a weight here. Since we do not have weight, then the no connection is represented as 0 and a connection is represented as 1. We have a connection from A to B, so we have represented it as 1, and similarly to A to C, so and so on. Now, directed graph representation. So the simple difference between the directed and undirected graph representation is we did not have a direction in the previous segment, but here we do have directions. So B is connected to A, but A is not connected to B. So we will write it as 0 because the control is traversing from B to A, but not from A to B. So we need to take care of the traversal of control. So we are representing as 0, and you can see from D to B, we have one connection and the traversal is in the direction of D to B. So we will have 1 there. So here we have D and B, so we have 1. So in that way, we represent the directed graphs. Next, undirected weight graphs. So this was what we discussed before. Instead of zeros and ones, we will represent the weight here. So we do not have a connection between A to A, so that is 0 as usual, but we do have a connection from A to B, so we have represented it with a number that happens to be the weight of the edge. And remember, we do not have the direction here. This is undirected weighted graph. Now, if it were the directed weighted graph, then we could have seen the direction and represented the number with the weight. Now, after this, let us look into the adjacency list. So what is adjacency list? Adjacency list is a linked representation. In this representation, we maintain the list of its neighbors for each vertex in the graph. Every vertex of the graph contains the list of adjacency vertices. Array of vertices which have vertices indexed by each vertex number. For every vertex, the array element points to the linked list of the neighbors of the vertex. So this might be a little complicated to understand, so let us understand this using an example. So directed graph representation implemented using linked list. So this is the directed graph we are using. So you can see that A is not connected to anything, so we have ended the address of next location as X, but B is connected to A and C is connected to A. Similarly, D is also connected to A. So that is how we represent the directed graphs using linked list. Next, we have directed graph representation using array. So A is not connected to anything, so we have represented as 0, and B is connected to B as well as A, so we have 1 there, and C is connected to B, so C is also connected to A, so we have 2 there. D is connected to A, C and B, so we have 3 there. Now we have the graph traversal. So graph traversal refers to the process of examining each edge and vertex in a graph. Graph traversing can be performed in 2 ways. The first one is breadth first search or BFS algorithm. BFS starts traversing the graph from root node and explores all the neighboring nodes. Then it selects the nearest node and explores all the new nodes. Queue data structure can be used in BFS algorithm. So the following image depicts the BFS algorithm working. It chooses the nearest node first, then it traverses to all the other nodes. So followed by BFS algorithm, we have the DFS algorithm, that is the depth first search algorithm. DFS starts traversing a graph from the initial node of the graph and then it goes deeper and deeper until it finds the node has no child. Then backtrack from the dead end towards the recently explored nodes. Stack is used for BFS algorithms. So this particular GIF image can be considered as the graph traversal which is performed using DFS algorithms. So if you don't know much about DFS and BFS algorithms, don't worry about that. Those particular tutorial videos are added in the description box below. You can go through it and understand BFS and DFS algorithms in a much better way. Now we will go through some of the applications of graphs. So some of the major applications of graphs are used in the websites, Google Maps, and social media websites like Facebook, and some security systems, and also software programming.
In this tutorial, we will learn coding workflow and some hacks for it using AI. Before that, let's take a quick look at what exactly we are planning to do. We are entering a new era where coding is no longer limited to seasoned developers. Thanks to groundbreaking AI tools like GPT, Claude, V0, and Cursor AI, the entire development workflow is being reimagined, making it accessible to anyone with an idea. GPT now acts as an intelligent co-pilot, helping users to write logic, debug, and explain the code in plain language. Claude streamlines the product planning phase by turning rough ideas into polished product requirement documents. V0 takes things to a step further by replicating any website from just a snapshot, eliminating the need for manual front-end design. And with Cursor AI, a more powerful IDE built on top of Visual Studio Code, users can describe what they want in natural language and see the entire application generated, refined, and enhanced directly within the editor. It doesn't matter if you're a non-technical professional, a digital marketer, or an aspiring creator. These tools break down the barriers of traditional coding. If we can describe it, You can now build it faster, smarter, and without even writing a single line of code from scratch. That's exactly what we're going to discuss today. And that said, if these are the type of videos you'd like to watch, then hit that like and subscribe buttons and the bell icon to get notified. Also, just that you know, if you are interested in upskilling yourself, mastering generative AI and artificial intelligence skills to land in your dream job or grow in your career, then you must explore Simplilearn's cohort of various generative AI courses and certifications. Simplilearn offers various certification programs in collaboration with some of the world's leading universities like Purdue, IIT Guwahati, and many more. Through our courses, you will gain knowledge and work-ready expertise in skills like advanced Python, machine learning, generative AI, and over a dozen others. That's not all. You also get the opportunity to work on multiple projects and learn from industry experts working in the top tier data and product companies, along with the academics from top universities. After completing these courses, thousands of learners have transitioned into an AI and machine learning role as a fresher or moved on to a higher paying job and profile. If you are passionate about making your career in this field, then make sure to check out the link in the pinned comment and description box below to find a generative AI program that fits your experience and areas of interest. Now, without further delay, let's get started. AI is transforming the way we program by acting as an intelligent assistant that understands natural language and translates it into the code. From generating entire functions to explaining complex logic and debugging it in real time, AI empowers both beginners and experienced developers to build faster and smarter. It's like having a coding expert available for 24/7 right inside your editor. Now, the tools that we will be discussing today are as follows. Let's begin with the first one, which is the Cursor AI. Cursor AI is a next generation AI powered IDE built on top of Visual Studio Code. It is designed to make coding conversational. It allows users to describe what they want in plain English and instantly generates edits or enhances code within the editor. With its Ask and Edit with AI features, Cursor AI turns your ideas into working applications, making it an ideal tool for both non-coders and experienced developers looking to accelerate their workflow. Proceeding ahead, we have the next tool, which is Claude. Claude is one of the top LLMs out there, and we will discuss its features. Firstly, natural language understanding. Claude excels at interpreting complex prompts and turning ideas into clear, structured content, perfect for planning software projects. Second one is product requirement drafting. Use Claude to write detailed product requirement, or also known as PRDs, without needing technical expertise. Context-aware assistance. It handles long-form inputs with ease, maintaining coherence across large documents and iterative edits. And lastly, the seamless collaboration. Claude is like having a thoughtful co-founder. It helps shape your vision into actionable specs for design and development. The third important tool that we will be discussing today is called as V0 Dev. So V0 is one of the tools out there which can recreate your front-end development just by using the snapshot. Following are some of the important pointers, starting with UI from screenshot. V0.dev can instantly replicate a website's layout and design by analyzing just a screenshot. No manual HTML or CSS needed. Prompt to UI generation is the next point. Simply describe your desired interface in natural language and V0 generates production-ready React code. Third one is built for speed. It drastically reduces front-end development time, letting you to go from idea to UI prototype just in minutes. Perfect for designers and founders. Whether you're prototyping fast or launching MVPs, V0 bridges the gap between vision and front-end code effortlessly. Now that we have a detailed understanding of theoretical knowledge on these three tools and how AI assists in programming and coding workflow, let's now dive into the practical demonstration where we will use these tools to understand how exactly they help in real time and the coding workflow. Firstly, we have the Cursor AI, the code editor, which is built on top of the Visual Studio Code by Microsoft. You can say that just by the interface. The interface completely matches with minute enhancements with Visual Studio Code. And this particular tool is a trusted partner of Shopify, OpenAI, Replicate, Perplexity, Midjourney, Samsung, and many more. Downloading Cursor AI is really simple. Just go to the version that you need to download for. For now, I have Windows, so just download the exe file and just run the file and you will have the Claude AI editor in your system. Once downloaded, you will have this particular home page where you can start with a new project, clone a repository directly from GitHub, or connect with SSH. Now on the right hand side, you can see we have the options. So it is connected to an agent, right? And apart from that, you have the ask and manual features. So when you're running with agent, you just have to write a prompt here. For example, let me write down a prompt, a simple prompt. Build me a tic-tac-toe game using JavaScript, Bootstrap, HTML, and CSS. That's it. And now send it. Cursor AI will automatically create folders all by itself and build a program which is ready for execution. Let's wait for a while and allow Cursor AI to generate all the code documents that we need. While the Cursor AI is building our tic-tac-toe game, let's also explore the other tools like V0 and Claude. Now we are on V0. Let's write down our prompt. So our prompt will be, can you recreate a website using the snapshot? Now here you have the attach option. You can upload from the computer, also choose Figma. Now I'm selecting this particular screenshot which is similar to Spotify and go. V0 is analyzing and there you go. It is also providing the ideology it's going through. And now the code will be generated within a couple of seconds. There you go. V0 has successfully created multiple files and it has segregated all the code files into their respective folders. And apart from that, it has also created a sample template here, which you can run in localhost. So your front end is now ready. Now, apart from recreating existing websites, if you wanted to create a website from scratch using the code documentation, or let's say you have the product requirement from your client, or let's say you just received an email that the client requires a particular product, then you are preparing it from the scratch, starting from the product documentation, then you have the help of Claude here. Now, let's create a new window of Claude and let's give the requirement in natural English language in one single paragraph as a prompt. So here is my prompt. So now I want you to help me scope out the product requirements for a new web app that I want to build. So it should be a very simple lightweight testimonials management application. And the way I want to collect the testimonials is basically by providing a Notion template, because Notion has this feature now where you can collect forms and this is stored on Notion and basically acts like a database. And then I want one feature which basically takes the testimonials in the database and just creates a static HTML embedded link so that you can embed these testimonials on any website. And then I want another feature that just creates nice exportable JPG images of each of those testimonials. Right? Now this is my prompt. You can go ahead with it and run. Now Claude will provide you a detailed project requirement documentation, and if you want you can make some edits to it, and if you find it too complex you can simplify, and if you're comfortable with the product requirement documentation that Claude just provided you, you can just copy paste it onto V0 and get an application developed instantly. So let's go through it. So there you go. I think I want a little more elaboration. So I'll pass this as my second prompt. Now let's execute it. So there you go. I'm good with it. Now it sounds good. So write me a product documentation from this so that I can start designing the application. Now it gives me an end-to-end project requirement documentation which I can directly copy and paste on V0 platform and get an end-to-end website designed. There you go, it's ready. Now what I can do is just copy and go to a new window for V0, and now I can directly paste it over here and ask it to run and create me a new website. As we have already seen in the previous execution, V0 automatically segregates the code into separate files. It creates an entire documentation and it creates an entire folder of all the code segments and prepares the application or website ready for us. Now it's processing. Let's give it a little time. Meanwhile, let's have a look at the previous execution in Cursor AI. So it's still running, maybe some connectivity issue. So there you go. The website preview is ready here. Let's run it in the local host. So as per the requirements, we have our web page readily available using V0 Dev. Now let's get back to Cursor AI and see what's the progress. So there you go. I think we're almost done with the creation and it is now giving us some information about the process. I created a complete tic-tac-toe game with the following features. So it just took a little while. Don't have to worry about it. So now you just have to agree to all those things which the tool is giving you, Cursor AI is giving you. Now the game is ready. Now let's go ahead and run it in the local system. Now that the program is ready, go to the file index.html. Since it's HTML, you can just copy the file path. So now the path has been successfully copied. So just go to the index folder and just right click and there you'll have the copy option. Just copy the path. Since it's HTML, you can open a new tab in Google or any of the browsers you like and just paste the path and execute. Just hit here, enter. So there you go. We had some slight issues with the npm server installation. So it automatically did it. So I just gave the prompt. The game did not load. So it did the background processes which we need to do. So it also included the npm and it installed and it gave us some directions. So go into the location, navigate to the folder and double click on HTML file which reads index.html. And we did it, and after that here you go. So X is mine, so that's O. This is my input. So I won, player X wins. There you go.
And with that, we have come to the end of our full course. If you have any doubts or questions, ask them in the comment section below. Our team of experts will reply to you as soon as possible. Thank you and keep learning with Simplilearn. Hi there, if you like this video, subscribe to Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, you can check the description box below.